It's the more, it takes more time to do it. Yeah. Okay, so we are going to look at two things today. One is you guys have, at least several of you did, I mean, the rest of you don't know what you're doing, read the paper and posted the review. And the ones that were posted by like yesterday or maybe early today, I actually looked at them and already for some of you I gave comments. In general, the earlier you post, the more likely that actually if you post it, not earlier is not required. If you post by the night before, I would actually look at it, because it's unlikely that I would have time to. The whole point of it is if there are questions that are common questions between, from the perspective of what all you people are reading, rather than when I ask people, are there any questions? Nobody says anything. So I can, like, for example, these are some of the questions that I saw. So I kind of wrote them down. That sort of a thing can be possible. And also, again, this is a graduate class. Some people, I mean, what you get out of the class depends on what you put in. And my interest is, to be completely honest, in general itself, I have really not as much interest in making sure that the average is lifted. Graduate classes are for people who really understand. If you really, really understand, I'll spend more time with you. That's just the way it is. Your grade is different. Your grade doesn't depend on whether or not you're writing your papers with me as a co-author. That's not required. But on the other hand, the more you spend, the more I'm likely to actually spend time reading what your reviews are, etc. Okay. So I think the thing that's pretty well known for people is, and I'm still hoping for that to happen for me. I'm probably too old by now, plus I'm in the wrong field. S. Chandrasekhar is a famed physicist, and at some point of time, he used to teach this graduate seminar for just two people in Chicago, University of Chicago. How many of you heard this story? Okay. He used to wake up very early in the morning and then trudge through the snow to teach these two guys, the graduate seminar. And basically people said, why are you wasting time? I said, no, that's like they're like industry people. And then it so happened that those two got Nobel Prize in that area before he did. So this is the dream of graduate courses. Yes, what I'm saying. I understand the computer science, there are no Nobel Prizes, etc., all this stuff, but although AI seems to be an exception, so maybe there still may be some hope. But anyway, so that's my point basically is the more you put in, the more I'm going to spend time trying to figure out what you're doing. There's a minimum that everybody should get, but how much more you get depends on how much you're putting into the class. Okay, so the point for that is that if you post reviews when the reviews are required for the night before, then I'm more likely to have time to read them before the class. I'll read them by end anyway, but before the class. So basically, I also posted the current day slides, and I'm going to spend actually the progression, regression, and causal link as three different ways of checking whether a given plan is correct. Where we think about plans right now, essentially as, with respect to what we have, built up in the last two classes, and you are about to, by the way, I should remind you that there is a homework due, and that's basically writing PDDL specifications. It's not that hard. It's not exactly rocket science, but just so that you will write PDDL specifications and see if in fact planners can meet their specifications. Okay. So we will assume in general in this class that when I say an action, I kind of think of something like that. An action A1 has some preconditions, E1, E2, etc. And then Fx, E1, not E2, etc. Okay, that's the expectation. Okay. And then the idea would be that a plan in the end, in this representation, a plan in the end is just a sequence of actions. Okay, and of course, the other question is, this is the action representation, and the problem itself is being given by initial state, goal state, right? Initial state might be, like I might say, initial state is P1 is true, and goal state, I want P1 to be true. That would be your lucky day, because there the plan is very clear, right? Essentially, it turns out A1 gives it to you, right? Just the sequence A1, singleton sequence A1 gives it to you. I mean, of course, the luckier day would have been initial state is P1 and goal also is P1, in which case you don't even need a plan, actually, right? Anyway, so the idea being that basically this is the kind of thing, I mean, the actual problems might look more imposing or less imposing. We'll get to these things later. So for blocks world, for example, these things look like this. The P1, P2 are things like on table X, on table XY, on XY, clear X, hand empty, holding X. Those are the proposition symbols. Okay, and initial state is always completely specified in classical planning, right? That's like the starting point. If you don't specify the value of a variable in the initial state, that essentially means that there is uncertainty about the initial state. And if there is uncertainty about the initial state, that means you are not fully able to observe what is actually true in the initial state. Okay, if you can't observe with the initial state, then you're likely not to be able to observe any state. So in general, if a world is fully observable, that means you can observe every state. Then by definition, you should also be able to observe the first state. You understand what I'm saying? That's why initial state not being observable essentially means it's a partially unobservable or partially observable state. Okay, so we will always assume that it's fully observable, and so we will say all the things that are true in the initial state. And the other thing that we will do is we'll assume that the goals are essentially, they don't have it completely specified. The goals are, you say what you want and what their value should. That's it. This is the way normally people say, as I went through in the last class too. Nobody exactly explains what should be the state, the entire world's state when you pass this course. I just say pass this course, that's it. And the rest of the variables in your life, they will just fall where they may, essentially. Okay, so goal state is partial specification. So the example that we will be looking more for most of the time today would be this particular one, initial state, A is on table, B is on table, A is clear, B is clear, hand is empty. Okay, the goal state is not clear B and hand empty. And one important thing to understand is typically, because initial state is complete, corresponds to a picture. Kind of. Right? Goal state doesn't correspond to a picture. Do you understand what I'm saying? So a picture, essentially, one of the things, actually, the beautiful thing about what does language get us? Over and above pictures. You know what people say, a picture is 1,000 words? That's a bad thing about picture, actually. You see what I'm saying? Sometimes what you would like to do is just say a few words and let people complete the pictures in their head. Do you see what I'm saying? And so one of the interesting things about language, one of the interesting things about all formal reasoning systems, including, of course, natural reasoning systems like language, etc., is you say only partial specification of the words that you are interested in. So you start reading a novel where they will say it's a vivid novel. Even the most vivid novel won't give you pictures. And those of you who are impoverished in their imaginations will wait for the Hollywood movie to be made. Because there you don't need any imagination. Right? Because everything is shown in pictures in front of you. You understand what I'm saying? So in this case, initial state on table A, on table B, clear A, clear B, and empty. Hey, that's an extremely easy picture to draw. That's the picture. Right? Whereas, a second, whereas goal state is not clear B and hand empty. What is the not clear B? How am I going to draw not clear B? So hand empty, I can say, what is not clear B? There is B and something is on top. It could be like a giraffe which is standing on B. That also will make B not clear. Actually, the reason I say giraffe, honestly, is because there's a beautiful TV program that long back I saw about human language, and which basically, where that guy says, if you're into pictures, draw a picture of the following sentence. There is no giraffe standing next to me. That's the picture. That's all I'm saying. Draw a picture which corresponds to there is no giraffe standing next to me. Do you understand what I'm saying? We can reason with this stuff, but there is no picture. Pictures typically tend to be complete words. So from those of you who remember logic, right? I mean, again, I'm assuming that you're supposed to know logic. In the propositional logic, for example, if you have n variables, then the truth falsity interpretation for each of the variables will give you an interpretation. So there are 2 power n interpretations. Each interpretation is essentially like a complete word. If I just take a couple of things and say this should be true, that should be false, there are total n variables. Okay, let's say there are total 10 variables, and I give you valuations for each of the 10 variables. This is true, this is false, etc. Then that's just a single word. If on the other hand I say, well, no, variable 4 has to be true, variable 7 has to be false. That corresponds to essentially 2 power 8 interpretations. Do you guys see this? 2 power 8 interpretation, because you hold this and this constant, everything else can move between true and false. So that's 2 power 8 interpretations. In general, when you actually get the whole interesting part about logic, interesting part about language, is you get to describe things partially. Especially in the case of the goals that you want, you say, you describe partially, this is my dream, this is the kind of world I want to live in. I mean, even Martin Luther King did exactly say, I have a dream where people will be wearing red shirt, blue socks, and yellow pants, etc. He had a dream, a specific dream, plus a whole bunch of other constraints he did, other things he didn't actually specify. You get to see whether you are in a world where his dream is satisfied. You understand what I'm saying? So that's the beauty of language. It allows you to describe only the things that you know. In pictures, if you want to draw, it becomes extremely hard. It's like the picture sort of disappears in the middle, especially photographs. How do you draw a photograph that shows, take a photograph of a world that is incompletely specified? What does that mean? Do you understand what I'm saying? It's extremely important to understand that distinction. So notice that already here, I picked this goal because not clear B and hand empty doesn't give you right away a picture in your head. There are multiple pictures. For example, A sitting on B will make B not clear. You see what I'm saying? But there can be other things. If there are extra blocks and C can be sitting on B, that will also make it unclear. So in general, goal can be corresponding to multiple words. You see what I'm saying? Which also means sometimes that it's actually hard to tell whether any of those. So you need to be able to get to one of those words. That's one of the things that we will figure out in planning. Okay. So if you think in terms of graph search, right? In graph search, it's very easy to kind of try to think about, basically I have a start state here and right, and this is goal state. And find a path. Most people tend to think of planning as path finding. You see what I'm saying? But what we just said tells you that you never actually specify the single goal state. Typically, there may well be multiple vertices in the graph that correspond to goal states. And the real planning is starting from the known start state, which is a single vertex, and going to any one of them. Do you see what I'm saying? So in a way, it's harder than graph search. In the graph search, you know which particular goal you're supposed to go. But here you have to figure out what are all the goal real states that are consistent with the partial description I gave. And see which of them is the closest and get there. Do you understand what I'm saying? Again, these are all stuff you just take it for granted. I'm just making you think about it so that all these things will come in handy in understanding why certain things are hard versus easy. In general, for example, if you have a graph and you're searching it in the forward and the backward direction, there's no difference. Right? If you want to find a path from S to G, you can find a path from G to S, that will be fine too. Right? But if on the other hand, what you have is S and multiple G's, G1, G2, G5, and you want to get to any one of them, then all of a sudden, going from goal state to the start state is much more funny, much more complicated looking. In parallel, you have to start with all of the goal states and see which one reaches initial state first. Do you guys see this? That's what is regression. We will talk about progression, regression, class-based planning. That's what is regression. From an atomic state perspective, like simple atomic states. Remember we talked about atomic state first before getting into the propositional representation, etc. From an atomic state perspective, regression is already a weirdo thing. Because it's not like looking from one, a path from one state to another state. It's looking for a path from a whole bunch of states to the initial state, even in the case where full observability. And one of the things that you'll have to understand again, actually this graph search analogy is something that you want to keep in your head. But when we are doing planning in these propositional representations, in these relational representations, what would that have meant in a graph search scenario? It's the easiest to understand graph search analogy with progression. By the way, I'm assuming that you read those two chapters by now. Okay. So the progression is just going from S towards G. Right, quote unquote. But regression will be multiple goals and you're trying to come towards this. And if you're trying to actually look at a graph analogy, then you have to actually pick which complete state should I be looking for? You see what I mean? Otherwise, you have to actually have a different notion of graph search itself, where you're doing search in terms of space of states. It's like belief states. What we said belief state was essentially a set of atomic states. Okay, one of the other things I'll say is, I remember what I said in this class, and I assume that you are remembering all of those yourself. I understand that I'm doing this for 34th year, and you're doing it probably for the first year. So you may not, but in general, the more you can make the connections I'm making to the previous classes, the more you are to be. Okay. Anyway, so that's the connection with the graph search. But the point I was trying to make is writing in language allows you to talk about partial goal states. And today we will actually get to this famous Sussman anomaly, where I will tell you that in fact the quote-unquote anomaly goes away if you give complete state, more complete state. In fact, one of the weird things is when somebody says, all I need is for you to basically pass this class or something. You might want to ask, can you tell me a little bit more? should I still be alive by the end of the semester when I pass this class? Am I required to have approximately the same weight that I have? Should I have still boyfriends and girlfriends? Can you tell me what are your requirements in these kinds of words? The more you get that information from me, the better you can plan. But I would say, why do I care? I just need you to pass this. I just need you to get Nobel. That's it. The rest you figure out. If you understand what I'm saying. Okay. Yes, there was a question.
That's very
I see that's the usual way it happens. So, but please ask questions and no questions. So anyway, keep that in mind. And so we are going to look at this kind of a thing, and we are going to understand progression, regression, and yes.
For that example, because we have the context that it's on table A and on table B, won't we can't we infer immediately that the only scenario is A on top of B? Because
What does the infer mean?
like if the goal is not clear B, so B can't be accessed, and your hand is supposed to be empty.
Okay, so one of the things, this is the reason, okay, so without putting you on spot, have you taken intro to AI 471? No. That pretty much gives it away. And I understand, and please don't take it, as an insult to you. I know that some of you haven't, and it's actually fashionable not to take intro to AI. It's fashionable in some states not to talk about Plato and Socrates. In many computer science departments, it's fashionable not to take intro to AI. And that I relate to LLMs. Right? But the point is, if you don't know Plato, you will rediscover Plato, my friends. Right? Of course, you get to write newspapers. Similarly, if you don't know to intro to AI, you get to rediscover intro to AI. What you're asking for essentially is, can I not infer? Yes, you can. But computationally, such an inference can be extremely costly. Nothing comes easy. So in computer science, in the intro to AI, you look at my 471 notes, for example, 470 lectures, I'll basically point out that given a set of propositional axioms, checking whether something else follows for sure. That means in every world where these constraints are satisfied, this constraint will also be satisfied. That's basically propositional entailment. That for propositional logic, that's ONP complete. For first order logic, that is semi-decidable. Above first order logic, it is undecidable. I think the case about undecidable, semi-decidable, and just a bigger LLM will solve it. That's a crazier way of doing things. Like you understand, but it's important to understand. I mean, it's like the same thing about Plato and case about Plato and his cave of mirrors. I just find out myself by putting actual mirrors in real cave and do some experiment. That's like you can if you know the background, then you will rediscover it in the hard way. Okay, so that's the answer. Please do, so if you have issues with what I'm saying, if you are taking first instance, please do ask. And I'm not trying to put you on spot, but I'm trying to explain to you that you will learn stuff like this in 471 if you actually take it, especially with me. Okay, because I'm assuming that you're taking it. Anyway, so inference is not cheap. I mean, whatever you can do with inference planning also. One of the reasons actually why we, in fact, it's the same reason why we talk about strict assumption, right? For example, in these actions, pick up X, hand empty, clear X on table X, that has to be the preconditions. And after you do pick up X, you will be holding X, and X won't be on table, hand won't be empty, X won't be clear. You would say, hey, you already said holding X. And can't I infer that it's not on table? Yes, you can. But that would mean, given some things that I know about the state, can you tell me what are the other things that will follow? That's theorem proving. Theorem proving is ONP hard at the least, at the lowest complexity. Becomes undecidable otherwise. Do you see what I'm saying? You can do it, but it's like an extra cost, So that's why we have the strict assumption, which makes you basically spend time explaining exactly what changes and what doesn't change. In real world, normally you would just say what changes, And then the rest you would basically may be able to sometimes infer. There's nothing wrong with inference. I'm just saying it's costly. You have to understand that. This is like the cheapest algorithm that you can write, where everything has been given in the, in the description of the words, description of the actions. All you need to do is almost write state, action, next state, action, next state, action, and then every once in a while check if in fact the goal state happens to be true in the current state. That, my friends, is space complete. Can you give you that? Thank you. Thank you. By the way, so this poor guy gets like a badge. This is what I mean. You break a leg, you still show up. So anyway, so progression. So this is the actions. You understand this. These are the kinds of action descriptions that you're going to draw for various problems. I also wrote a version for like a slightly more complex world, the one-way rocket world, right, earlier. And in writing that, I basically tried to tell you that you can put some more syntactic sugar, such as conditional effects. The previous one is like the simplest. There's no conditional effects, nothing. And in fact, one thing where this is actually a little more than normal, what has been called the normal strips language, or the strip. PTL allows all of these, but the normal strips language essentially assumes that the only things that appear in all the fields, none of them have negation signs. They'll all be positive negatives. And what then basically it does is the preconditions always will be positive in strips action representation. Effects, since some of the things you want to, what was true before, you want to make it negative, you basically wind up having two effect lists. One called the add effect list, called the add list, other called the delete effect list, called delete list. You see what I'm saying? And so if you put add and delete, then you don't need to write anything negative. The ones that are going to be made negative, you put in the delete. You see what I'm saying? This is just a purely a convention. Just like a convention, like basically right-handed is the default, left-handed, B plus, semester, all that stuff. Similarly, positive is good, negative is bad. The polarity doesn't really, there's no actual value judgment here. Variable can take two values, true versus false. It's not that false is bad and true is good. No such thing. Right? For example, the state variable is volt and date. False is a great value. You see what I'm saying? True is a bad value. So that's my point. That delete is not that. Basically, the point about adds and deletes in the normal strips language is it makes it look as if goals should always be positive. But by going one step above and then basically saying effects can essentially just say what are the valuations of which of the state variables, I get to directly ask goals that I don't want B to be clear. And I want hand to be clear. And this is just, if you have something like this, it turns out that you can convert it into a strips representation by just increasing the number of state variables. Just as remember when I told you last time, if you have conditional effects and you don't like conditional effects, you could have split this particular action into, if there are like two packages A and B, you can say fly with nobody, fly with A only, fly with B only, fly with A and B together. And then there won't be any conditional effects. This is compilation. So in general, I would say one of the things that we will be seeing is these languages, they're all basically, you can think of programming metaphors. This language can be compiled into the strip representation if you want. Pretty much everything can eventually be compiled into the graph representation. So you can do path planning. You see what I'm saying? So these notions of compilation is actually useful to understand, and we'll also see that certain kinds of problem, this is like the domain models being compiled. But we can also compile, for example, like if you have a scenario, later on we'll find out that if you have a scenario where, let's say, the initial state is incompletely specified. That would lead to things like a conformant plan, which we'll talk about later. It turns out one way of doing it is to actually compile it into a huge number of classical planning problems. And if this thing is working, then you can use the compiled results to solve that. That's one way of actually solving computation. Of course, that is about actually generating algorithms to solve these problems. Remember, there is this whole other thing, that is, I take the problem and give it to LLM. And I just take whatever it is and then write a paper. And we will be doing both of them, as I said. But you need to understand how you would have done it without LLM so that you know how LLMs can screw up. You see what I'm saying? Okay. So anyway, that's the thing. And so the first part that we're actually going to do really is that given a plan like this, as I said, remember what I said, the minimum you need to search for something, right, is if that thing that you're searching for comes and bites you, you should say, yeah, that's not one, another one I'm searching for. If not, it will just bite you, you just throw it away and look for it still. You see what I'm saying? So in a sense, you should know what you are searching for. Saying that I'm searching for something that I have not defined to myself, yeah, of course, then you will never get that. Right? And so the point, of course, is if you're looking for a correct plan, then if the correct plan came and beat you, can you check if it's a correct plan? That's the verification. If you don't know the verification, then searching for it, you're just impressing your friend, saying, I'm busy, I'm looking for stuff. I don't know what I'm looking for, I'm looking for stuff. Those of you who never wake up and hang around at home, playing games and saying, I'm trying to search for meaning in my life, that's probably what you're doing. You have to figure out what it is. If the meaning came and beat you, you still don't know what it is. Right? I mean, that's fine to live like that. I'm not against it, But on the other hand, for planning, right, for any computational problem, you need to be able to check if a given artifact satisfies, is a solution to the problem. If you know, then you can invert the verifier to search for it. At the very minimum, I would say that if I can give you a gold test, if I can give you a gold test, the gold test basically checks an artifact and says, is this correct? As a solution test. Right? Then I can do at the very minimum, the dumbest idea in the world is generate test. That's it. Then generator generates an idea. Tester checks if the idea is correct. If not, it says generate again. You know what I'm saying? And if it says it's correct, then it goes out. Then it's an answer. And to the extent the tester is sound, that means, and sound and complete, that means it will pick every solution that is actually a solution. And will never pick anything that's not a solution. Then generate test is already a sound and complete planning algorithm. Any algorithm, actually. I'm talking about planning here, but really it can work for anything. Whatever it is that you're searching for, you should first know how to verify it, if I give you a potential answer. And once I give you the verification, then you can at least do it in a generate test. You see what I'm saying? And in fact, I would argue that, I already mentioned this previously, that generate test normally would be infinite monkeys generating, things, and then testing, checking is it Shakespeare, and then if so, sending it out. That is generate test. That's the usual thing. Infinite monkeys keep typing on the typewriter, might very well generate, Shakespeare, and as long as you have a Shakespeare detector, you basically see if they're generated. The big difference with LLMs is instead of monkeys, we now have LLM. And I don't mean it in a bad way. LLMs are much better at generating plausible-ish solutions. You see what I'm saying? So then I will use LLM as a generator and then do everything like this. That will be enough too. So basically, first thing I will check is try to tell you how you will check the plan is correct. And I'll give you actually, normally think of a simple scenario. You guys, sorting. Like whatever I'm saying is true for sorting too. If you are looking for a sorted sequence, I give you an arbitrary set of a sequence of numbers. You want to sort it. Right? So one idea is take a permutation and check if it is sorted. So the important thing before you get permutation, if I give you a sequence and I say this is sorted, can you check if it is sorted? That is a solution check. There are multiple ways, it turns out, of checking if a sequence is sorted or not. And every way of checking if a sequence is sorted, if you invert it, leads to a different sorting algorithm. The quick sort, the bubble sort, the selection sort, all of them are really different ways of verifying the sorted sequence, inverting it such that the search generates the solution that is eventually sorted. If you have any one of these verifiers, then you can always do a dump sorting algorithm, which is make a computation, check if it is sorted. That's already computationally sound and complete. In particular, if you have n variable, n numbers, how many permutations are there? What? In fact, that's all. And once you give a permutation, you can check if it is sorted or not and how much time.
O of n square.
O of n square is to generate the sorted sequence. N log n is also to generate the sorted sequence.
O of n.
Basically, O of n. So you have an efficient algorithm already that I'm telling you. At 310, this is what you should have started with, which is I have this factorial generator and factorial times n. And times n factorial is the dumbest algorithm that is already completed somehow. Everything else essentially is trying to kind of what is a name called finite differencing. Basically, it's trying to construct the plausible solution that will actually pass the test. That's what algorithms do. Computer science algorithms do that. And for every way of proving the correctness, there is a way of doing this. Okay, much of what I'm doing is I'm talking about planning, but I'm also trying to mess with your minds in terms of how to think about algorithms in general. But any that you are interested, you need to first understand how to verify. And for every way of verifying, there is always a dump search, which will always work, generate and check. The other is try to make this verification, compile this verification somehow into the generation stage, such that will be more efficient. So what happened in the sorting algorithms is the dumbest sorting algorithm is n factorial times n, but you are able to get up to n log n by just doing it efficiently. And you are now thinking, why did we waste all this time? Because now what people do is give the sequence to a ChatGPT and say, sort it. It's no skin off your nose. Okay, but keep that in mind. Okay, so the question then is, so this is why I'm going to tell you at least three, there are many, many ways, but there are three canonically classical ways of checking whether a sequence of actions solves a planning problem. Whether a sequence of actions solves a planning problem. And there are three verification procedures. Each of them you invert, you get a different kind of planning algorithm. Progression one, you invert it, you get progression verification, you invert it, you get progression search. Regression verification, you invert it, you get regression search. Both of them are fairly easy to understand. Progression is very easy, regression is tricky. Then the plan space one, if you invert, you get plan space planning algorithm, which, historically people would find that extremely painful to understand the search. It's not that hard if you understand what you're trying to do in terms of verification. Okay, that's what you're going to do. So I'll again basically look at it from the perspective of this rocket algorithm here because I just have pictures for that, but we could have done this for the block swan algorithm, block swan problem. So in the case of progression, what the idea is that because you have the state, initial state is complete, each action tells you what should be true in the state before it, and will tell you what will be true in the state after it. So you can what is called progress a state over an action. And the progress is just almost an algebraic operation. It's very simple. You can only progress the action if, in fact, what it says in the preconditions are already true in the state where you're trying to apply the action. If so, then the new state will have everything the action says in its effects, plus anything that it doesn't mention in its effects, you just copy it over from the previous. Do you get that? The copying part is important because there can be a million state variables. This action just says, I'm only going to touch these 10 of them, and they will be having these values after me. So you actually put them in those valuations because that's in the effects part of the action. And then million minus 10, you just copy it over from the previous. That's progression. And you do that next after that, then you do the next action. So if I say load A and load B as the action, as my sequence, then I'm progressing load A, I get this state, then I progress load B, this state through load B, I'll get this state. And if in fact my simple goal is A should be inside and B should be inside, then I can check if in fact in A and in B is true in the final state. Notice that I basically, so the point is actually I'm also, So the states should be, one of the things is this is a complete state. And because it's a complete state, after the deterministic action, you will again get a complete state. And you'll get a complete state, etc. So when you start from a complete state, you'll only get complete states. And you just have to check if any of the complete states happens to satisfy the goals you are looking for. The goal is just basically evaluation over state variables. I want this to be true, this to be false. You're checking that. There was a question for that. Yeah.
As you said that copying is very important. So does it cost you something?
No, again, these are what is it cost something? So you are ready to look for, I mean, not you, but lots of people may be ready to say, n factorial guesses we'll see. That is the real cost. Okay. All we are saying is if you want to project an action, you have to copy the rest of, you have to know what happens, what is the current state and what happens to you. Everything costs something. The question is overall, what is the complexity of it? There's another question.
Yeah, so for the definition for see if the goals are present, are you talking about the sub goals that are specified in the goal state?
That's it. That's it. Because remember, we made the general idea again, A star search, those of you who did intro to AI, A star search does this in a more opaque way. It basically says there is a piece of code called goal test. You give it the current state, it will say yes or no. If it says yes, you are done. If it says no, then you are not done. From the perspective of A star search, planning is a lot less opaque. It is telling you what it is asking you to achieve. Do you understand what I'm saying? Those of you who did 471 actually will remember that A star search is specified for arbitrary problems in the goal test. Because of which actually in doing backward A star search is very painful. Right? Because you don't know what backward A star search even means. You only know how to go forward and check if the state actually satisfies the goal test. In these cases, both in CSP problems and in the planning problems here, I'm actually telling you what I'm looking for. I will say that the state will always be of this form, each variable and its valuation, true, false. And then I'm looking for a kind of a state where 15th variable is true, 17th variable is false. And if you ever find that, you're done. Yes.
If only some of the sub goals are satisfied, so like maybe like one of the three are satisfied, is the whole plan considered invalid?
No, it's not done yet. Yeah, so it's not a solution, right? What I'm saying is, imagine the, you are at a state where you have basically, again, one of the funny things about writing, one of the funny things about writing states this way is there are n sub goals typically in the goal state. Right? Because there are n, you the n sub goals, let's say n being the total number of state variables, and the goal state may have just mentioned m of them. In this case, 2 of them. Right? And so you can think of them as each of them are my sub goals. Right? The question, it is a very, very interesting question. We'll get back to this, but you can start thinking about what the implications of this is. If you are in a state where n minus 1 of the sub goals are satisfied, but the nth sub goal is still not satisfied, it's still not true, it's not a goal state. Is it? Is it a nice looking one? Yeah, it's a nice looking one. You may use it as a heuristic to still look for the real state. Okay, I mean, like the two sub goals, be rich and happy. You take some drugs, you're already feeling happy. So all that's left is the rich part. The point is, both need to be true at the same time. Okay, so in general, when you have n sub goals, it is very well possible that some of them are harder to achieve than others. Even weirder, if there are n sub goals, one of the weirder things that happens is if you think, it's very commonsensical to think in terms of, I will make, since there are n things to do, I will do the first thing. And then wherever I am, then I'll do the second thing. Wherever I am, I'll do the third thing. Wherever I am, I'll do the fourth thing. You see what I'm saying? This is like the simplest idea for planning. The simplest idea for planning, and it's called means ends analysis plan. So you have n sub goals, you check your current state, see if any of the sub goals are not true, then pick one of those sub goals, try to make progress on it, get it, now that sub goal is true, then from that state, try to achieve the second sub goal. Then from that state, achieve the third sub goal. Some state, achieve the fourth sub goal. How easy would the world be if you can do this? Most of the reason when such a thing is possible, you don't need planning. Right? Because essentially, what happens, what stops this from happening is when you try to achieve one sub goal, after you have that sub goal, then from that state you try to achieve the second sub goal. You might undo the first sub goal. You see what I'm saying? Like, and so by the time you got the second one right, the first one is gone. I mean, it's not, none of this is surprising. I mean, you guys know search, right? I mean, you at some point of time saw really bad things like Rubik's Cube, and you still survived and came here. And Rubik's Cube, it looks extremely like a solution. I'm almost about to declare victory. So I just need to get this in the place, I'll make cover. Oh, everything is done. Right? That's why Rubik's Cube. Imagine Rubik's Cube. Okay. Essentially, you can remove everything and put it in the correct order yourself. Right? It's an easy Rubik's Cube to buy and feel good about for about 3 microseconds. After they say, what the heck? I mean, I should do something more interesting in that. I think the real Rubik's Cube is really, really painful to do. I never touched it. But, the one where you can just put things in the correct order yourself. Right? Even better, like, I'll give you a white Rubik's Cube and I'll give you colors. Red color badges, green color badges, yellow color badges. You'll be so fast. Right? Weirdly enough, hopefully by the time we are done with the class, I'll say that standard LLMs do that kind of Rubik's Cube well. When all sub-goals, each sub-goal can be independently, you can find a plan for each of the sub-goals independently, and interleave them or concatenate them or put them together any which way, and you can be sure that all sub-goals are satisfied. That's the type of search problem LLMs excel at. because there is no search. You understand what I'm saying? In fact, how many of you remember in the paper that you read, there is a section that I will talk about today too, about where we remove the preconditions and also delete lists of the blocks world and point out that LLMs do better. They were just looking for a world where which is easier than blocks world. Right? You see what I'm saying? And the easy part is in those worlds, mean sense analysis just works. Because if you have n sub goals, you can get n sub plans for that. And then you splash them together any which way you're done. Those are the kinds of worlds planning is not really needed. You are lucky if you have such kind of planning worlds, but then you will also feel very bored and then move on. Real world is not like that. Okay, so this is again the point. Now, interestingly, notice that when I talk about progression, regression, and plan space planning, I still would act as if I'm not actually going to be talking about the fact that the goal is really multiple sub goals. I'm basically just checking to see if all of them are satisfied. The question that she was asking is, like, if some of the sub goals are satisfied, can that somehow be used? In the verification stage, no. But in the search stage, maybe. Because you can say, if you have two states and you're trying to decide which state to expand, you might expand the one that almost has all the sub goals. That's just a heuristic. There was a question somewhere. Yes.
I was gonna ask, is there any similarity between, or like, are they synonymous between like sub goals being non-interacting with each other and the ergodic?
And then what?
The ergodic, like.
The ergodicity is connected in the sense that in a non-ergodic world, sub goals must be non-independent, but not vice versa. In blocks world, sub goals are already not independent. In blocks world, sub goals are not already independent. And yet in blocks world, you can never get into a state from which you can't come out. You can always, it just becomes a more inefficient one. Let me actually, skip a few slides and get to those many slides I'm going to skip and then get to mean sense analysis mostly there. Okay. Yeah. Because I mentioned mean sense analysis. It's there in one of the later slides. I'm going to bring it up first. Historically, this is what was the first planning algorithm. By the way, STRIP stands for Stanford Research Institute Problem Solving System. And Shaky the robot was using this planning algorithm. Okay, and and this is Shaky, the algorithm, and this is yours truly. It's in the computer, not the algorithm, Shaky, the actual robot. And this is in the Computer History Museum in San Jose. You can go see it. Okay, and this is the guy that was using STRIP's planning algorithm. So they were actually trying to get a robot to do some things, and they, for a robot to do something, you need it to do plan for it and execute it. So as part of that bigger project, they came up with the STRIP's representation as well as STRIP's planning algorithm. STRIP's planning algorithms is the mean sense. What it used to do essentially is it puts all the goals, sub goals that I showed you. I'll come back to progression, regression, and plan space maybe, but let's listen to this first. Okay. Put them in a stack. Go sub goals in the stack, some arbitrary stack. Okay. And then pop the stack. So you know which goal to work on. Try to actually just make that thing be true. And you can do this recursively. To pop the clock, suppose you pop G1, then you look for an action that gives G1 as an effect. Action A1. So you put A1 on the stack instead of right now. Okay, but then A1's preconditions now come on top of it. Because if you want to do A1, then its precondition must be satisfied. Then you put them in a stack there, substack, and then you start popping them. This is basically what I mean by saying work on each sub goal recursively until all sub goals are being achieved, at which point you declare victory. But the problem is, if you declare victory that way, you would actually be wrong. Right? This is what I'm saying. Right? So, interestingly enough, and one of the reasons I bring this up also is science is a human activity. There will be papers that are written that are actually wrong, and everybody say looks good, looks good, looks good, until somebody points out there's some problem and say, I understood now, it's no problem, and then they study it. The only difference between science and religion is when somebody points out there's something actually wrong, you're supposed to realize that and then actually change course. The fact that you haven't seen anything wrong until somebody actually pointed out collectively is part of science, because we always thought, that there was ether that is required for light waves to travel. And there were people writing ether papers for a bunch of time before everybody collectively realized, yeah. You see what I'm saying? So anyway, so this paper is extremely well-cited paper. It turns out how to solve problems, planning problems, and then it turns out that this will work. And in fact, one of the interesting things it does, you can look at this more carefully, but it basically does allow for when you have G1 to Gn, it even allows for every, you can backtrack over the permutations. So because you're putting them as a stack on a stack, right? So you need to decide a permutation. So it will first put like G1, G2, G3. If it fails, then it'll come back and say G2, G1, G3. If it fails, comes back and say G3, G1, G2. So it will consider all permutations. Now it looks like then it should work. Okay? But it's not even just a simple going forward. It is actually considering changing the permutation of the subgoals at every stage. This is a nice recursive algorithm. And what's more, poor Shaky, by the way, it was called Shaky because it used to shake a lot when it was trying to move from place to place. Poor Shaky was solving problems left and right. It was actually stacking blocks left and right in 1972, the 69-72 time frame. And papers were written. In fact, one of the earliest papers in artificial intelligence journal is a STRIPS planning paper, and it's very well cited. Obviously, basically it's a very important thing. Now, the problem, unfortunately, is STRIPS is incomplete. That means there are problems which can be solved, but STRIPS, it can't be solved. That is where Sussman anomaly comes. Okay, Sussman, by the way, is Gerald Sussman. He's the professor at MIT, and when he was doing his graduate study, he then came up with this particular planning problem. This one: C is on top of A, B is on table, and I just want on A, B, and on B, C. Actually, this picture I should show you. Remember, I'm supposed not to show you pictures. This is picture I show you. C is on top of A, B is on table. All I need is on A, B, and on B, C. Those are only subgoals. Now you can actually figure out what happens. If you, let's say, try to work on A, B first, right? Even basically just you can see what happens. You will take C off, you put A on top of B. Now you are in a state where C is on table, A is on top of B. So on A, B is already true in that state. From that point, you want to get on BC right. So then to get on BC right, you need to take A off, put B on top of C. At this point, on AB is gone. You see what I'm saying? So let's see. So what is happening in this particular case? Actually, no. So here is the deal, actually. In fact, the thing is that you don't, what it does is it basically considers solving it in the order on AB on BC, or solving it in the order on BC on AB. And if one of them, if the solution is not right, it'll just give up. If none of them, the solution is right. Okay. So if it tries on AB on BC, after getting on AB, then it gets on BC, then on AB is no longer. So that order didn't work. You should notice that I could have gone forward from that, but that's different. That's different from actually just only considering the two, two permutations. If on the other hand, I try to do on BC on AB, given my state, I'll put B on top of C. That's the nicest plan. At that point, to get on AB, I will have to put everything back and put A on top of it. Once again, BC is done. All I'm trying to tell you is whichever order in which you solve the sub goals, you're dead. In fact, there is a beautiful word for this. It's called serializable sub goals. Serializable is actually more constraining than independent. Independent subgoals means that you can get a plan for each of the subgoals and splash them together in the plan for all the subgoals. Serializable is actually more constraining. It says there exists some order of the n subgoals such that if you follow that order, then you'll never have to backtrack. So if there are n subgoals, then there are n factorial orders. One of them, if the problem is considered serializable, if any one of them works, that means you just basically, in that order, you make the first goal true from the state, you make the second goal true from that state, you make the third goal true from the state, you make the fourth goal true. And when the nth goal is done, you say done. That's basically what Scripps algorithm does. You see what I'm saying? It turns out it took a long time for people to realize that Scripps algorithm, first of all, basically everybody was happy, and then Sussman came along and said, hey, give this problem to your Scripps planner and see what happens, and then it fails. Because neither order works. So then they had to make up a new theory. And the theory was, well, if it is serializable, then it will work. The question is, given a set of subgoals, how easy is it to check if the subgoals are serializable? You understand what I say? Here's this magical algorithm that if you give it a serialization order, then you just go through each of the things and then it declares victory. I just need to know whether it is serializable and what is the serialization order. Well, it turns out running it on Scripps and seeing if Scripps fails or passes is the only way to check if it is serialized. There's no cheaper way. Did you understand what I'm saying? This is computer science. This is the interesting thing. We might actually explain what are the subclasses where the algorithm will work, but checking whether you follow that subclass sometimes might actually involve running that algorithm. You see what I'm saying? So to actually check if a set of subgoals are serializable, you just give them to Scripps and see if it solves the problem. If it says, then say, oh, it must have been serialized. If not, oh, of course, it's not serializable, can't you see? Do you understand what I'm saying? Okay. Now, one more thing about this is, this is the reason why the picture part is important. So actually, you should forget about that picture. I shouldn't have given you the picture. I normally just say on AB and on BC. And you assume this picture. You assume this picture. But it turns out that in fact, C in the A is also a reasonable picture. A, B, C floating about in the world is also a goal state. If you in fact have a D, C being on top of D would also be in a goal state. You agree? So the picture is wrong. You should never think of a goal state as a picture. Now, if you do decide to get a picture, and you say, so I said, this is my goals, this is the goals that you have to do. Then you might keep pushing me to say, is this what you mean, Rob? Imagine you said that. Then I say, I can't deal with your pestering. I say, yes. Then it's obviously serializable. You know why? Because this is a complete picture. I can actually write as on AB, on BC, on C table. If you have three subgoals, there is an order such that you can achieve each subgoal in that order, and by the time the third subgoal is over, you're done. Do you guys see this? This is what I mean by saying, paint me a picture of your goals. Is asking people to do more work, asking the user to do more. Like just as I said, I want you to get A plus in this course, and you say, paint me the picture of my life, where I will get an A plus. You see what I'm saying? And then I have to write a picture with lots and lots of stuff in your world has fallen apart. You have no girlfriends, no boyfriends, no sleep, nothing, and you still have an A plus. Then you will just work on that. Of course, that could also be a problem because you might very well say, first let me lose a girlfriend or a boyfriend because that seems like a part of some goal. Okay, and then you will still not get an A plus. That's a whole entire different story. Okay, but the point is, if you are making a goal state be a picture, you're forcing the user to give more information. The guy who wants you to do something. All they want it is, I want A and B and C. I don't care about the rest of the stuff. You figure out, man. And if you do that, it's non-serializable. If on the other hand, you actually give a full picture, then it is serializable. I would argue that in no reasonable planning scenario, would you have a complete goal state. You see what I'm saying? Like, you think of robotic planning. This is basically robotic planning. We'll say, I want A on top of B. What else am I expecting? I don't have to give you a picture. I just have to say, that's the thing that I want. And here is the complete state you are in. I gave you eyes and ears, so you can sense the state. And I want you to get to a state where you're holding the block. This particular spoon is in this. This ladle is in this dish. You say what you want. You don't say, I want this plus everything else about the rest of the world. Here's the picture of the rest of the world. If you do that again, planning becomes easy. Weirdly enough. You got that? If you actually got that, even for the people who understand planning, etc., you are in a very small minority. The tricky part of actually normal planning is I just tell you what I want. Which is a very reasonable thing it looks like. Just tell me what you want. And when you say, right, draw me a picture, then you are forcing me to tell you more than what I want. All I needed is A on top of B. Imagine a different version of this. C is on top of A, B is on table, and there's a D and a E and an F and a G and a H and an M and a K. Right? It will still be a Sussman anomaly problem. By the way, you guys agree that it will still be a Sussman anomaly problem. What happened? Yeah.
As somebody who's specifying a goal state with lots of sub goals in it, how will I know that I've completely presented the complete?
It's your problem. There are two very different issues. There are two different issues. Okay. You can see it from both sides. Did I mention Midas, King Midas? King Midas basically said, all I need is whenever I touch anything, it should turn gold. Right. But then he kind of didn't quite realize that if people actually literally make his goal true, then when he kind of holds his wife or his son or his little doggy, they all become gold. Maybe he liked golden wife, golden dog, golden son, but most likely he probably did because gold also means they're dead, right? And so you didn't know what goals you really wanted, but asking that guy at that time, draw me a picture doesn't still help. Because what is the picture for the goal? Turn everything I touch into gold. There's like zillion words, depending on what are all the things in the world. So you are talking from the point of view of the fact that the users may not know what their goals are. That is different from once they say, this is my goal, you pestering them and saying, give me more information, give me more information. That's what I'm getting to. So if in fact there is on C, A, B and E, F, G, H, I, J, K, then to draw this picture, you need to know where C is. So you will come up with many stacks. A, B, where some of them have A, B, C in the middle and they stop above and stop below. Some of them will have A, B, C on the top and there's a whole bunch of stuff below. Some of them will have, A, B, C in the bottom and they stop above. All of them are goal states. Pestering me to say, where should this other thing go? Like, for example, so you're saying I'm supposed to get A plus, but I want to get married. How do you think I should get married? I don't care. It's your life. In fact, the point of planning is everybody puts their demands on you. You, the intelligent agent, decides how to satisfy those demands or say screw them. I am not going to live your life for you. Everybody puts their requests on you. In fact, one of the things we'll talk about in a very quickly, a little later, is this idea called oversubscription planning. Oversubscription planning is right now classical planning is if I give you n sub goals, you must satisfy all n sub goals. Otherwise, you're not a plan. Oversubscription planning is I'll give you n sub goals, satisfy the maximum you get. You see what I'm saying? And in fact, I can actually have cost considerations. That is, doing things has a cost, making the goal happen has a reward, and I may want to just maximize my net benefit. When people give up on some of the things, forget about homework 5, man. I mean, there are more important things in my life than homework 5. You have decided that your life is oversubscribed. You're saying screw to homework 5. You coming to me and say, don't you understand? I have a life. Please don't give me homework 5. That's not my problem. You see what I'm saying? That's not my problem. In general, life is not, the world is not set up to make sure that your life is easy. You, the intelligent agent, decides what sub goals to achieve and what ways to achieve. Okay, yes.
I think I'm a little confused on the definition of describing a goal state completely. Like,
But in our case, if there are n state variables, you must give the valuations of each of the state variables in the final state. That's it.
so would you have to say like clear A, not clear B, not clear C as well, in order to have the goal state completely described or no?
What?
Like, do you have to say clear A?
Yes, actually, in fact, that's true too. In fact, in this particular case, you're right. The full goal state, the complete picture is clear A, on AB, on BC. That's enough, actually.
Do you have to do like not holding or?
No, that's an interesting point. It turns out that you don't, for each of, so if you want to really give the complete state, you are actually right that for every one of them, you have to give the valuation. Which is actually true. I was just giving you a more easy to understand thing where you realize that on ABC may be somewhere inside the middle of the stack. But he's actually right that, by definition, all I can say is saying C's on paper is a more complete specification of the role. If you want a really complete specification, you have to give evaluation for each of the state variables. And one of the tricky parts then is it's my problem. Right? Do you understand? It's like I'm going to ask you something and you put the burden on me. Hey, I'm fine, man. I'm going to do whatever you want. Just tell me everything else in my life, what their value should be. That's basically why, if I do that, then your life becomes easy. Okay? It's a good question, by the way. You guys understood this? Yes.
In the previous slide, you talked about the permutation part. If a plan fails to achieve a serialized, if strips algorithm fails to achieve a serialized plan, then it uses a different permutation of a stack. Is it part of a conventional strips plan or is it a modification?
No, that's a strips, normal strips plan. So basically, there is a backtrack point in the strips where you can actually change the stack. Basically take the sub goals and put it in, take a permutation and put them on the stack. And if you fail, come out of that, then you will put a different question on the stack. That's the classical strips server. And by the way, so the interesting thing is because of this, if strips actually misunderstood the difficulty of planning problems and it came up with an algorithm that actually doesn't solve all the planning problems, even in this simple language, being good researchers, you say the problem is with the problems, not the algorithm. Right? So my algorithm is good. If your problem, that's bad. Okay, so then you talk about things like you have non-serializable subgoals. That's why I can't solve. And there is another terminology called linear versus non-linear planning. Non-linear planning. Non-linear planning and planners. And the idea is linear planners essentially assume serializability. And they'll only work with the serializability rules. And if the plan and nonlinear planners don't assume serializability. The weird, mind-boggling thing is this is 1972. Okay. And I actually came here because the discussion led me there, but really all I wanted to do is tell you about progression, regression, and plan space planning. Okay. And all I'm saying is all three of them are actually complete. If you start by checking how to verify a solution and either use a full generate test or draw an algorithm which actually completely satisfies, basically will consider all possible ways of satisfying the verifier, then you'll get a complete algorithm. So progression is so much simpler to understand. It's actually better than strips. Regression is slightly harder to understand. It's actually better than strips too because it's complete and sound. Plan space planning is even more painful to understand for some people, but it's also fundamental. See what I'm saying? Okay, so progression basically you go like this. Regression, you start from the goal state. Remember, the goal state is actually not a single state. It is just a propositional formula that might be consistent with many states. Okay, and then you regress. And we need to talk about what regress means. To regress, one of the things we do, let me show you this. So first of all, progression is like this. And I actually can, let me show this too. Progression for this particular problem, to do progression, I start from this state. If I know the way to check the progression verification, the way I can invert it is consider basically growing the prefix of the plan. Remember, the only way you can do progression is if the prefix is a value. You see what I'm saying? You must have a prefix. And you have a prefix, then you take the very first action, do it in the state, you'll get a next state, then you do it in the next state, you'll get the next state, etc. So consider constructing the overall plan in terms of its prefixes. That's progression. Consider constructing the overall plan in terms of its suffixes. That's regression. You see what I'm saying? So if you just have the progression verifier and you have an LLM generator, it will just come up with an entire plan. And you can check by verification to see if it's correct or wrong. And if it's wrong, you say try it again. That will be generate test. If you want a more efficient algorithm, you generate the candidate itself in such a way that it actually is constructed is kind of customized to the verifier. And the verifier is basically going to be able to project the prefix from state to state to state. So you construct a prefix. So progression search, not surprisingly, looks like this. This is the most obvious search that you thought about when you thought about planning. But I'm just getting you here from a very roundabout way, saying that this is just one of the many things. It's not even the first thing that people tried. The crazy strips algorithm is the first thing people tried. Okay, so in this case, you have pickup A, you get this state, you get pickup B, you get this state. And then essentially it becomes a search algorithm. So you have to then pick up one of these states. If you're doing A star search, these will be in your open list. You have to pick one of the states and then expand it. The goal test is if in any of the states the goal is already true, not clear B and hand empty is already true. Okay, so here neither not clear B nor hand empty are true, because instead of not clear B, you have clear B true. Instead of hand empty being true, you have hand empty false. So this is still not a goal state. Similarly here, not clear B part is true, but hand empty is not true. So neither is this a goal state. Because this is not the way A star search works is it picks a node from the open list. If it is a goal state, it stops. If not, then it expands it. The $1 million question is if there are many, many things on the open list, which one are you going to pick? And that's where we came up with the heuristics idea. And we will talk about heuristics next class. And we're going to read some reading material about sub-goal interaction-based heuristics, which we'll discuss in. But right now, assume that there is any example would tell you go this direction, go that way. A smart answer. Okay. And so this is progression. Right. And again, I'm mentioning Script's assumption is if an action changes a state variable, it must be explicitly noted in the action. Yes. Regression is more interesting. This is generic progression planner. So goal test as G, check if every state variable in S that is mentioned in G has the value that G gives it. Okay, and child generator, essentially, if you think in terms of A-star search, for each action A in the set of actions you have, you try to see if that action can be applied to the current state. If so, what would be the new state? And then you put that new state in the openings. This is how you generate a tree of states. Right? And then your search starts from the initial state. The next is regression. Right? So the interesting thing, regression basically is that I am going to apply the action in the backward direction because regression essentially tries to check if the plan is correct by starting from the goals and computing what are the weakest preconditions that must be true before this action, such that after the action, the goals will be. Any of you know about program verification? Have you ever heard of things like program verification? In program verification, you take a program and check whether the program is correct or not. By the way, programs are complicated plans, honestly. Okay, so one way of actually verifying programs that nobody does anyway, the theory of program verification is like Dijkstra's verification, for example, is weakest preconditions. So there is a specification for the program. It must do the following thing. You then try to compute weakest preconditions for each statement in the program such that before that statement, that must be true so that after the statement, the goals will be. And in the case of programs, you also have to compute this for loop statements. But thankfully, we don't need to do for loops. And then when you get the final weakest precondition for the entire program, you check if it is already true in terms of the input specification. That's how you prove a program. This is called, programs are proved by regression. You see what I'm saying? And so honestly, I would just start from this and I'll start from not clear B and hand and T. And then I will consider putting actions in the backward direction. What does backward direction mean? If this is the last action, what must it do? If this is the last action, at the minimum, it should screw up any other subgroup. If you're the very last person to leave this group, right, then after you leave, nothing is changing. So if a subgoal is already, made false by you, then that will stay. Right? So the minimum is for, just as to apply a action in the forward direction, you check its preconditions are holding in the previous state, then you will apply it. In regression, to apply an action in the backward direction, you check that none of its effects are inconsistent with the goal state. That means they are not actually violating any other subgroups. Because if it violates, imagine if this guy says, for example, consider put down B. Okay, if I do put down B, right, as the last thing, if I do put down B, that's actually, so that if I do put down B in the last thing, then after I do that, B will be on table. B will be on table and hand will be empty. And B will be clear. Remember, put down B will give B to be clear. But I want B to be not clear. So if I put down B as the last action, I'm screwed. It cannot be. Do you understand what I'm just saying? That's why there is no put down B in that picture. That's why I put a question mark. You basically just syntactically check that put down B has an effect, not as one of its effects, clear B. A subgoal says not clear B. So one of its effects is actually exact opposite to what I do. So this can't be the last action. That's the minimum requirement. First do no harm. If you have the last action, first do no harm. The second is maybe do something useful. Okay, so the second condition is at least one of its effects supports one of the subgoals. That's being useful. If you have to give up on one, you can give up on the usefulness. You'll just have inoptimal plans. They're useless actions that are not doing anything. If you give up on inconsistency requirement, then you will actually have plans that won't work because the last thing kills subgoals. You guys see this? Right? So, interestingly, enough. This is basically how you do regression. Just as for progression, it's very simple. For the action, all its preconditions must be true in the previous state. And then you construct the next state by copying the effects, first writing the effects of the action, and then copying everything else from the previous state. For the regression, on the other hand, a state can be regressed over an action A if there is no variable V such that the V is given different values by the effect of A and the state S. This is the inconsistency part. Yes.
Can regression plans can also be considered as recursive plans? Like we keep.
There is no connection between regression and regression. Recursion is an algorithmic point. Regression and progression is whether you're doing action in the backward or the forward. You can actually do recursion in both ways. Essentially, you can do progression recursion. You have an initial state. I need to go to the goal state. I can basically apply some action, I'll get a new initial state, recursively see if this new initial state to goal state is possible. That's recursion. I mean, they have a lot of common RE and SSION, but unfortunately, they're not the same. But please ask questions like that. There is at least one variable V dash such that V dash is given the same value by the effect of A as well as the status. That's being useful. If so, you will put that action in. If so, you put the action in. At which point, the resulting new state, I still have to compute the new state. In the case of progression, it will just be copying, basically put the effects of the action and copy everything else from the previous state. Here, what I will do is I will take all the subgoals that action hasn't given, copy them over. Because if this guy hasn't given them, it still needs to be satisfied. So put down A gives me the only useful thing that put down A gives me is hand empty. Right? So not clear B will still have to be true previously. Right? And then because I'm trying to do put down A, I better have the preconditions of put down A satisfied in the previous state. Recursively. That basically means put down A requires holding A as a precondition. So the way you compute the regressed state is you take the original goal state, remove all the subgoals that this guy is already supporting, and add all it, and then keep the others back, copy the others in, and then add all the preconditions of the action that you are putting. Now, what is the goal test? Whenever these goals are already satisfied in the initial state, you're done. Do you see what I'm saying? The idea is previously I'm taking initial state towards the goal. Here I'm taking the goal state towards the initial state. The beauty is the initial state is actually a single vertex in the graph. And so you're actually going vertex to vertex to vertex to find a state which satisfies the goal test. Here, when I'm doing this, honestly, there are potentially many states that have this property. But many complete states that have this property. And what I'm doing is I'm folding them as a bunch and computing another set. And any set of subgoals will basically be corresponding to more than one state. Because if there are n state variables and you only have m subgoals, then you have 2 power n minus m complete states that are consistent with it. Right? And I can stop as soon as if my current initial state already has these things, then I can stop. That's regression.
Well, then you can, but then in that case, if you have
a state of multiple initial states?
There's only one initial state. Remember, this is classical plan.
Oh,
Yeah, I said it only 18 times, but you should remember that. You know, in classical planning, they only have one initial state. Remember, I did say that, right? Yeah. There are many goal states, many complete goal states consistent with the goal, but there's only one initial state. What you're thinking of would be more relevant when we get to conformant plan.
no,
We'll do
what
that.
I'm saying is that like in regression, you're going the other way.
How does it matter? Initial. Here is the I, here is the G. I going from G towards I or going from I towards G doesn't change I and G. They are what they are. I and G are given by the user who said, this is my initial state, this is my goal state. Algorithm doesn't change the specification. If so, that would be essentially saying, I'll just make the problem that I can solve against the problem, instead of the problem you asked me to solve. So for both of these, the initial state is exactly that and the goal state is exactly that. Whether it's progression or regression. Again, please understand the following things. First of all, I appreciate the questions. Secondly, understand something as simple, as dumb and simple looking as progression search and regression search that you thought you understood, probably, I mean, if you paid attention, has lots and lots of interesting issues. And understanding that will deepen your appreciation. And it also basically makes you less impressed by every damn paper, right? Because if you don't know how anything is actually, what is difficult versus hard, everything is surprising. My God, it looks in LaTeX, must be good. That's not the way you read papers. You see what I'm saying? You know, it's not, it's like a paper, honestly, in scientific terms, a paper is not to be published if it is impressive to just you. It should be published if it is impressive to the humanity. Right? It expands the humanity's knowledge. And we chose 3 bozos as reviewers and say, you are the representatives of humanity. And if the reviewers are not really shining examples of humanity, oftentimes first-year grad students, unfortunately, are not, and they do all the reviewing for Neurips and iClear and ICML, it's them saying, yeah, that looks good, man. And it gets. You see what I'm saying? Basically, that's what science is all about. It's not, it doesn't really matter. I have mentioned this here. For science to proceed, one person should have a true idea, and one more person should be able to, one more person, hopefully younger than them, should understand it. Then the science will proceed. We can all just buy an easy chair, relax. The rest of us are just trying to play, you know, like from the sides. Essentially, this is what I'm saying. If you want to be a contender, that's the issue. Are you getting something that is expanding humanity's mind? Okay, anyway, that's regression. Here is an interesting question. In progression, I know that we are running a little late, but I will want to complete this and then we'll give a break. In progression, as you go forward, everything is a complete state. There is no such thing as an undefined state. Right? Because initial state is complete. You only apply an action if its preconditions are actually satisfied in that state, in which you will get it, in which case you will get another complete state. You see what I'm saying? It may not be a good state, you may not like it, it may not be close enough to a goal state or something like that. But if there's nothing wrong about, it's not like the state doesn't exist. On the other hand, unfortunately, in regression, that's not true. Because in regression, what we are calling, we are misusing the terminology. I'm saying initial state and goal state, and I said goal state is not a state. Right? Initial state is a complete state, goal state is not really a complete state. So goal state is really a set of complete states. When you allow a thing to be set, one of the subsets is empty set. Do you understand what I'm saying? One of the subsets is empty set. So in fact, I could have had a goal saying A and not A, like, you know, clear B and not clear B as my goal state. regression will still progress on it. I mean, go do search. But you know that you're never going to be able to get a plan for that. Right? Inconsistent goals. The interesting thing is probably most of the top level goals are actually consistent. First of all, one of the interesting things, let me tell you the following thing. Users can give, in fact, that's whoever that guy is. What's your name? Nived. So as Nived said, when users specify partial goals, sometimes it's actually possible that there is no real world state that corresponds to that partial specification, because they didn't bother actually completing that complete state. So it may even be possible that it's an unsolvable problem. Everything that I am talking about, honestly, should deal with an unsolvable planning problem. If I give it a planning problem where the goal state cannot be reached from the initial state, it should say so. That's part of being a sound and complete algorithm. Every classical planner, I forget about strips is a problem, right? But the progression and regression will, in theory, tell you if a problem is unsolvable, it tell you it's unsolvable. Right? And one of the funnier parts of LLM solving problems, planning problems, is LLMs have been RLHF to death. So they want to agree with you. You must have asked for this plan. You probably need it. So I'll make it happen anyway. Anyway, I don't care about it being correct or wrong. So I'll give you something that will actually work, that looks like it will work. So in fact, one of the things, I don't know whether I am sure we wrote it in the paper that you read about the accuracy on the unsolvable instances. And the accuracy on the unsolvable instances sucks even more compared to accuracy on solvable instances. Do you understand what I'm saying? And you might say, why would you take a planning course and deal with planning problems that don't have solution? Right? If you are a cybersecurity person, or if you are the guy who is designing Death Star, you are trying to make sure that there is no plan that Harrison Ford can use to blow up Death Star. So your planning is on checking that Death Star blown is an unsolvable planning problem given your world model. You guys understand this? Unsolvability is just as interesting as solvability.
So that became the goal.
What?
That became the goal.
Yeah, you can actually say, I mean, basically, no, given a problem, no, it's a meta point. Let's say, I'll give a planning problem, and you have to show that it doesn't have a solution. Unsolvability should be shown correctly. By the way, it turns out that it turns out that let me write it there, that you may have heard about NP complete, NP complete. Boolean satisfiability is an NP complete problem. That means given a set of propositional variables and a bunch of propositional constraints, can you give me a valuation of the variable such that it satisfies all the constraints? That is an NP complete problem. Okay? To actually prove that given a set of propositional formulas, that it will actually lead to, it entails another propositional formula F1. That is, you want to do theorem proving. The way you do theorem proving, you take these propositional formulas, you take F1, take a negation of F1, add it here, and say there is no world in the hell where everything I know as well as not F1 is true. That's actually how many of you know this, by the way? How many of you have done theorem proving in, this is the sad situation. I'm kind of doing a huge amount of remedial education here. You're all supposed to know this stuff. If not, you will get to reinvent. Right? So theorem proving is saying essentially that the reason this stuff leads to this theorem is because there is no possible world where this stuff is true and the negation of the theorem is also true. That means if I take the negation of the theorem and add it to this, I want to show it is unsatisfiable. Theorem proving is unsatisfiability check. So if satisfiability check is NP complete, unsatisfiability check is co-NP complete. You see what I'm saying? Everything that you're trying to solve, sometimes showing that it's unsolvable is just equally important, and you need a good algorithm should be able to do that. If it's sound and complete, it should do it. Now, why did I come up with all that stuff? Here, standing in front of you is a goal state that has an empty extension, effectively. It's dead. It looks good, but it's dead. If one of them said clear B and not clear B, you say clearly it's dead. That's not what it's saying. It's saying things that look like it is feasible. This is exactly what your boss does. They do G1 and G5. And it turns out G1 and G5 are quote unquote mutually exclusive. There is no world where both can be true. If you have a state which is not actually ever going to be used, so even if this problem is solvable, the problem is that when you're doing search, these sub-problems, some of them can be unsolvable. Do you understand what I'm saying? If you did check that it's unsolvable, then you extend it. And the way search becomes bad is dead nodes get more dead nodes, get more dead nodes, get more dead nodes. A huge, big dead tree. In fact, the way to do search is fail first. If you know something is going to die, quickly remove it. It's a bad idea. As against continuing all possible ways. Once it's dead, it's dead. Now, in front of you, do you see that one of those states is dead actually? Who knows? Who can see that one of these states? I mean, this is just block 4. There's A and B and a hand. It's simple. I mean, this is one of my, no, not you. So one of my, I'm proud of this example. I made it maybe 10 years back. It's as simple as it gets, and there's actually a state that cannot be reached. Yes.
Not really.
Not clear B and holding A. Why? In this world, so it's not that not clear B and holding A is impossible to achieve in any arbitrary world. But in this world, there's only A and B and a hand. From the initial state you have where A and B and hand, there is no way in the hell of getting B to be not clear. The only way B to be not clear is to have A on top of it. At which point you're not holding A. Interestingly, if you give this to ChatGPT, it might even say, no, I know that you want to solve this problem, right? I'll just put A on top of B and keep holding it. That's what I'm saying. In fact, once we're done, I'll show you an example like this that actually I made that showed up in the New York Times. And then when reasoning models came along, No Brown basically tagged me and said, Rob said LLMs can't do unsolvable problems. Look, O1 does it. Because unsolvable problems are known to be hard for standard LLMs in general. And in fact, the example that I showed there, even though it's actually unsolvable, GPT-4 GPT-401 or something, GPT-01 or something, gives me a wrong answer and tries to convince me. Then, it's okay, can I hold A on top of B? That way, A is being held and B is still not clear. You are happy, I'm happy, you're happy. And any of you who played with ChatGPT know that basically try to make you happy. If you gave a problem because you want to show you. In fact, if I said, show that it's unsolvable, it probably would have given another answer. They generally have a higher meta thing to agree with, especially the standard algorithms, not the ones that we make. So do you guys see this? This is dead. If you did not realize this, you would do search underneath this. It will become like a huge, big ASU sized, subtree. And you're saying, Mom, I'm making progress on my thesis. It's dead idea giving rise to other dead idea that's giving rise to even more dead ideas that are giving rise to even more dead ideas. You're dead and you don't know it. Do you understand what I'm saying? This is an issue. Let me do one more thing. I know that, now that you heard two ideas, progression and regression, you haven't yet heard plan space plan. And forget about LLMs for now. Just think of search algorithm. Which one do you think is going to be? If you want to write an algorithm, which is a better thing to do? Going forward or going back? You do know that there is a difference, right? So for example, if you wanted to see, if I give you a genealogy tree, and if I want to ask, is Tom an ancestor of you? Your genealogy. Which way would you go? You can start from Tom and go down. And if Tom is particularly fertile, you will spend a lot of time searching all over the genealogy. Right? On the other hand, biologically, everybody has only two parents. You go backwards, the branching factor is actually smaller. I mean, you learned so many new things in this class. If you ever need to figure out if Tom is your ancestor, don't start from Tom. Start from yourself and go backwards. This is well known, right? Because a graph can have forward branching factor different from a backward branching. Keep that in mind. So, progression versus regression from the branching factor perspective, it's no contest. Progression is I woke up in the morning. What all can I do? Consider doing each of them and see whether any of them leads me closer to goal. If you are in a reasonable world, you can do a zillion things. Checking if any of them is leading towards goal is, again, without heuristics right now. It's such a waste of time. Very high branching factor. Regression is for you on Fridays, the goal is at 1:30, I should be in the Rouse class. Start from there. Go back. So much simpler. Do you understand what I'm saying? Regression wins hands down in terms of branching factor compared to progression. Right? And in fact, regression is quote unquote goal directed. Because it starts from goal. And in general, everybody will say goal directed search is the best way. You don't just do things from where you are and see if any of them lead to something. You start from what you want to achieve and go back. But on the other hand, progression search will not lead you to states that just don't even exist. Every state in the progression search tree actually exists. In fact, even more interestingly, if there are n state variables, there are only going to be 2 power n possible states. If you check duplicates, then the entire search tree cannot have more than 2 power n states. Right? Regression actually searches in the space of partial states. How many partial states are there? If there are n state variables and I'm defining partial states as the state only mentions a subset of the goals and their values. It's 3 power n. Why? Because you need to, for each state variable valuation, there are 3 possibilities. It's part of the goal. It's part of the goal with positively. It's part of the goal with negative. And it's not part of the goal at all. The value. So the search tree for regression search is actually 3 power n. So much for your intuition about branching factor being small. Do you agree? So the two things I mentioned that, I know, first of all, I mean, you might say, I don't want to do regression anyway. Who wants regression? Because, who wants regression? Because this thing looks pretty, impossible. Right? Basically, you want to make sure that the last action is not actually removing anything important and it's giving something useful. But if you still do it, first of all, this is a lower branching factor. But it has this problem of getting to states that are not actually feasible. Now, smart ones among you might say, why can't we have a routine which takes a partial state and says it's not feasible? Right? You call that, it says no, then you just kill the plan. How hard is that? You already know it's hard because only 3 or 4 of you actually even figured out which of those 2 states are actually not feasible. The rest of you are like along for the ride. With 2 blocks, just remember that. Tell your mom that I'm in PhD programs and MS programs, I still don't know what the heck happens in 2 blocks. That's your cognitive limitations. And I mean that in a good way. All of us have cognitive limitations. You understand what I'm saying? So it must be hard. How hard is it? The only way to check that one of these states is actually not reachable is to make this the planning problem. I and this as the planning problem and show that it's unsolvable. Do you understand what I'm saying? There is a curious analogy between what I said. If before giving a problem to strips, you just want to make sure that it is actually serializable. But the only way to check if it is serializable is to give it to strips and say whether it got the solution, in which case then now you can solve it. Similarly, in this particular case, it would be very nice to kill partial states that are actually not reachable. In fact, the word reachability is an extremely important concept. It's not that this and this are somehow logically impossible. It is that this state is, given these domain dynamics, this state is not reachable from the initial state. And the only way you could figure this out is actually implicitly do planning and realize that there is no such plan. Do you see what I'm saying? There are special cases where you may be able to find them. For example, clear B, not clear B is one of those unreachable states and you can easily check. All I am saying is that making sure that every partial state that is unreachable is killed is out of question. So you might actually come up with sound but incomplete procedures for pruning. These are pruning procedures. So sound but incomplete, if it says it's unreachable, it's definitely unreachable. That's why it's sound. But it might say, it might not say it's unreachable, but it's still unreachable. That means it's not actually capturing the unreachability all the time. Sound but incomplete is fine. Unsound but complete, no good. Because unsound for incomplete is like, it feels like I don't like the looks of this partial state, I'll kill it. Right? In which case it's possible that that's the only direction to the plan. Do you understand? Yes.
I have a question about the bidirectional approach.
What?
The bidirectional approach.
We didn't yet talk about bidirectional. When did you talk about bidirectional?
I guess I just slide.
Oh no, I mean yeah, you can no yeah, when you're talking about that slide. I just put both of them together. I didn't yet really talk about yeah, you can do that. Yeah, you can do, yeah, you're right. Okay, sorry. Yeah, tell me. So you can also do bidirectional search where basically if anybody on this fringe is actually present in anybody in this fringe, you can stop. Because this is reachable. If this is the real state, I'm constructing a fringe of reachable frontier. And these are goals. I'm constructing a fringe of weakest preconditions. If any of the weakest preconditions are satisfied in any of the frontier reachable states, then I have established a connection. That's the plan. Yes.
So assuming like there's an approach where we're generating these states from the left side, like the regression side, and like these states from the progression and regression. Is there a guarantee that at iteration number 3, let's say it is solvable, right? Like let's just also assume it's also solvable. At iteration number 3, is there a guarantee, or iteration number k, that there would be some overlap? What if this went one step ahead and the regression?
No, I mean, yeah, that's it. No, I think that's basically the point is if your question is if this thing comes inside, that means if this is 3 layers and this is 3 layers, and it turns out that the last layer here is in the middle of the layers here. First of all, it's important to notice that I said frontiers because you can stop as soon as the frontiers collide. Okay, but if you're lazy, then you can say that actually, say, if I give you a big regression search tree and a big progression tree, then if any state in the progression tree contains any node in the regression tree, that's enough. It's not hard. But if you're doing it efficiently, you'll stop as soon as the run. Yes.
In the genealogy example, Tom and you, if you do the regression and trace your lineage back, but simultaneously also, is that like
That's bidirectional graph search. Yeah, it's not hard to do bidirectional graph search when I know S and G. The trickier part is in the planning case, I told you the goal state is actually a set of states. Think of what I'm doing, how painful you think regression is. Think of doing it in atomic states. In a graph, basically, as I said already, instead of this kind of a thing, this is G, this is G, this is G. There's a profusion of G's. If you have profusion of G's, and if you're doing, if you're doing a simplistic search, then you have to pick a goal state and try to make that happen. It may well be that that actually cannot be reached, or it's actually hard to reach, whereas one of the other ones is easier to reach. In a weird way, this is kind of connected to, very metaphorically, it's connected to paradox of choice. But that's smaller. Basically, there are like multiple goal states, multiple complete goal states are consistent with your goals that the user wants. And if you're doing backward search, and if you're doing search in the space of normal graph search, then you have to first of all pick one of them. Or do a parallel search from each of the G's. That seems like a worse thing than just going forward from S. Weirdly enough, many people who come from the graph search community, when they first understand anything about weakest preconditions and regression search, they think, wow, that's possible, huh? Because I'm actually allowing multiple states and I'm holding them and then regressing them. And sometimes that states will become unreachable. Okay, that's about progression and regression. I will stop here. We'll take 15-minute break. Then we'll come back and talk about the paper that you read and some of the comments on that. And then when I come back next time, I'll do the plan space part as well as the heat space. Okay. Yeah, I think this is what I'm going to do. I'll take this part of it is because your grade, I think, depends on whether I remember. In life, everything depends on people remembering, honestly. right? So if you are, if I remember you for the bad reasons that you're mostly asleep, yeah, that's okay, that would be easier. So it's better to know the name. So I will be taking a thing with my pictures. So that's good. Anyway, so two things before I go forward. I know we're going to go to the actual discussion of the paper that you read, which again, they have obviously not, I was hoping that there's a half of the class would be for it, but we had enough things to do before. We'll come back, as we did. But two things I wanted to mention are actually one very important thing is as somebody was, I mean, I mentioned this before, but I just want to kind of make you realize. Yeah, make you realize that. So somebody was asking this, that this is a complete state, and I said, when you do this action, you'll get the complete state, right? There are like two reasons and then the issue of it is going to be a complete state comes from the fact that the action is deterministic. Because deterministic action take you from one state to another state. That's it. Right? That you can compute the complete state easily as a doctoring operation comes from the fact. Let me just 1 second. Comes from the fact that we have Strips assumption for the actions. Strips assumption for the actions make sure that every state variable that the action touches, it should say exactly how it changes. And because of which, you can basically just pick up A and you already know that holding A, it says holding A, it says not clear A, it says not on table A, it says not hand empty. You write them first. And then for every other variable in the initial state that's not mentioned in one of the red variables, you just copy it over. They'll keep the same value. The only question about the strict assumption essentially is you might have said, it's a very reasonable thing, and I mentioned it before to you too, that there are connections in the state variable. So in fact, one of the interesting things is it looks as if state variables are axes to a higher dimensional space. Okay, each variable, that's the same thing, features, right? If you think in terms of machine learning features, each feature is an axis. And a data point is a vector in the feature space. So here, these are basically Boolean features. The interesting question is, if in fact, the variables make an orthonormal basis, I'm kind of combining things, unfortunately, because some of you know more about machine learning than about logic. So I'm also using those connections. Everything is connected. So if there's an orthonormal basis, that means that they're actually all orthogonal. That means there is no connection. Anything you know about one variable doesn't tell you anything about any other variable. Do you understand that? That would be orthonormal basis. In general, features are not independent that way. They always have connections. If they have connections, you can write the connections. In a logical sense, I can write something like this. For all xy, holding x implies not clear x and not on table x and not on xy. You understand the simple first order logic. It is just a domain axiom. There are two things. The fact that the domain axiom exists tells you that the features are not independent. Right? The fact that features are not independent also tells you that subgoals are probably not going to be independent. You see what I'm saying? Okay. And the second thing is, if they are dependent, then knowing about one feature lets you the value of the other features. In this particular case, pretty deterministic. There's nothing stochastic. So if you don't have strips assumption, then you can write actions in a much simpler way, which is just say the most obvious effects they have, and then let the theorem prover figure out what else will be true given the background domain axioms. Things like this would be called domain axioms. You just write it once. That way, this is like good software engineering practice. Right? If you're thinking of PDL models as a program, it's much better to write some of these domain axioms upfront so that you don't have to remember to make sure that because you are writing the description of the action, you are writing it, right? So you may forget some obvious things because they are obvious to you. You see what I'm saying? But if you don't do it, then basically if you have domain axioms, then what you need to do is after you write what pickup is main effects are, then you need to call a theorem prover and ask, tell me, given the domain axioms to know, what else do you know given what this is saying? You understand what I'm saying? That is basically theorem proving. And the answer basically, in fact, there is a beautiful word that all of you should know because it's actually very important to understanding notion of reasoning itself is this idea called deductive closure. Beautiful word. Next only to ergodicity, if you want to make your LLM bozos be, very worried about me, like you want to intimidate them, you say they are not good at deductive closure. And they can't say because they don't know what it is most, unless they took it from here. Okay, what is deductive closure? Essentially saying, given a data, and logical knowledge base KB, then if it entails a fact F, then you have to write every fact F that is entailed by the knowledge base, should be written. And the reason this is difficult is sometimes, imagine, again, logic, some logic at least because they are computer science students. Imagine you have A implies B implies an A, and C, A implies B implies C, and this also has a Q, and C and Q implies J. Right? Now, what is the deductive closure of this? Because A is true, A implies B is actually true. Because B is true and B implies C is actually true. Because C is true and Q is true, J is actually true. This is the closure. Closure is everything that can be derived knowing what you know. Everything. In a learning perspective, people basically, one way of thinking about it is that something that I tell you is it in your deductive closure of what you know, or is it not? You understand what I'm saying? So let me tell you a joke. So there are two infinitely, AGI-filled robots are playing a chess game. How does the game go? So, robot one does some number of tokens, charges it to Sam Altman and makes him. Robot two spends some tokens and says, I lose. That's it. Game is over. You understand what I just said? Chess is a dumb game, honestly. Because I'm bad at it, that's why I think it's a dumb game. But chess is a dumb game because chess, everything is in the deductive closure. It can be derived from the initial state. If you do an intro to AI, you would have learned about game trees and min-max, etc. And you can talk about forced win, forced losses. Sometimes after the first move itself, maybe it is possible that there's no way you can win. And this robot basically just gives up. The reason you still play is because you don't see it coming. This is what I'm saying. The car is coming hurtling towards you and you're trying to walk. Just do the deductive closure. And it will close you instead of you computing it. Because deductive closure is a computationally expensive procedure. For propositional logical databases, computing the deductive closure will be QNP hard. For standard logical databases, computing the deductive closure would be semi-decided. If something is in your deductive closure, that means that you are just already know it. You just didn't. Like, for example, if you had this in your database, that means you know this already. You agree that you know this. Okay? Somebody comes and says J. somebody else comes and says M. Are both of them giving you new knowledge? For a guy who can't do the deductive closure, both are new knowledge. I didn't know J was true. It is true that I'm stupid. I should have done the deductive closure, but it's true. I mean, it's not stupid. I should say stupid. I'm computationally, I have other things to do. It takes time to compute the deductive closure. So J is true, but I figured it out thanks to you, faster. M, on the other hand, was never true. Not from anything I knew. If you're telling me M is true, that means, wow, you gave me new knowledge. Do you see what I'm saying? This is inductive learning. And this is deductive learning. Deductive learning is kind of a dumb idea because you already know it, but you don't know that you know it. Inductive learning means you never knew it. Until I told you, you would never have had an idea that this was possible. Do you see what I'm saying? This is kind of important to know. This stuff is kind of important to know in understanding what it means, for example, to talk about generalizability. In reasoning problems, it turns out that what is important is in machine learning, we'll come back to it again, but maybe you must have heard about it, this nonsense about OOD, out of distribution. In versus out of distribution. The problem is, there's many things that are out of distribution. Right? And if it is, the more reasonable question is, if I give you an example, let's say of last letter concatenation problem, and I showed you how to do a 3-word last letter concatenation. The question is, have I showed you effectively how to do the 5-word last letter concatenation or not? If you think I haven't, then you get to say, you only showed me 3-word concatenation problems. I did new 3-word concatenation problems. I have improved my generalizability. But most of us will say, oh my God, I mean, this is such a simple procedure, and you should have realized what the procedure is and be able to actually solve every problem in the deductive closure. All of them are essentially the same. So in versus out of distribution is less important than understanding the notions of deductive closure for reasoning problems. You start from one small place, but everything in the world is kind of connected. And since it's a grad class, I get to do that because you better than where else are you going to go? Right? Okay, so that's an important thing I wanted to bring up. It also is connected to the fact that to avoid the deductive closure, you are nicely assuming the strict assumption. And that way you don't need to do any deductive closure computation. Okay. Okay. So this is the rest is actually, with respect to, I read some of the things that as of 10 o'clock were posted. So, and I have some questions that came up. I'm going to do with respect to the paper that it's a paper I wrote, right? So obviously I know too much about it. And I looked at your questions, and I essentially also put some connections to what you might want to say. We are starting slow. This stuff will be discussed multiple times anyway in this paper. So that's why I wanted to read it now itself. But a couple of things that table came up with, some of the questions that are reasonable is, well, mystery domain is bad for LLMs, but is it fair to check LLMs, make LLMs solve mystery domain problems? Because people may also not be able to solve mystery domain. Right? That's one of the people asked, and maybe some of you thought about it. It's a reasonable question. There are two things I will say. One is I'll actually tell you that we did studies with humans doing mystery domain problems. We have institutional IRB things so that I can do human subject studies. And I'll show you that in the next slide. But the bigger thing I want to make beforehand is this tricky question of what LLMs are supposed to be able to do. What are LLMs supposed to be able to do? Are they only supposed to be able to do the lowest common denominator human? In which case, why are we taking credit for solving math Olympiad problems. You are talking about humans not being able to solve mystery domains, so they may not be a fair question for LLMs. But you are also celebrating the fact that GPT-5 and even GPT-4 was doing fine with some math Olympiad problems. I can guarantee you that there are more humans who can actually, given money, solve mystery black hole problems than humans who, even if I give them money, they can't solve math Olympiad problems. Do you guys understand this? It's important to understand the asymmetry in expectation. You see what I'm saying? So basically, there is this thing that if it succeeds, you give it credit, whether other humans can do it or not. If it fails, there are humans who also will fail, so it's okay. That makes no sense because it's not clear what your expectations are on this system. So I want you to keep this in mind. You see what I'm saying? Having said that, how much ever of please don't ask me doesn't help. So you should actually say, in this particular case, it's not that hard to realize that mystery domain problems people can actually solve. Okay, the pencil, that basically, essentially, if you remember that system 1, system 2 metaphor that I had in the beginning class, we all have system 1 and system 2, essentially. Okay, and we would like to stay by with system 1. But if push comes to shove, right, we will use system 2. I mean, as I think what's his name, Bertrand Russell said, some people would rather die than think, and many do. Right, especially thinking is so painful that they would rather not do thinking. But we actually have the ability to think to some extent. So the question is, how do you incentivize? Give them money. Right, so in these experiments, we basically said, look, here are the problems. And if you are right, you'll get some points. If not, you won't get any money. Just taking part, you'll get some money, but getting the correct answer, you get extra money. Yes.
Isn't this baseline different from what was done in the paper? Because large language models were just given, or they weren't split into 2 phases of plan writing and translation. They were just given the mystery domain app by itself. They don't necessarily know, the correlation between the actual block sport and mystery block sport, all the reads.
They don't. We didn't tell them it's a mystery block sport. We didn't call it mystery block sport. We just said this is a domain. Yeah, of course. Of course. If I tell them it's a mystery block sport, by the way, hold that thought. So it is important to know that, this is written up in the appendix somewhere of that long paper, that we never told them. We said these are planning domains, PDL domains. And in fact, for most people, they don't know what the heck is PDL. You guys are kind of losers. You are in this class, so you might know, oh, it's PDL. PDL probably means block sort. So let's see if it's a mystery block sort. That's what you might see. But most of these people, they not. Okay. And but if you give them money, they basically solve it. We also try to give money to LLM, saying, okay, you're wrong, but we'll give you some money, will you do better? It didn't do it. It actually gave the money to Sam. Okay. My point essentially is the ability to actually spend time to solve a harder problem is possible for humans. I'm not saying block sport is as easy as mystery block sport for humans. I'm saying they can solve it. Just as math Olympiad is not as easy as 4 plus 7. Some humans can solve math Olympiad. You understand what I'm saying? Okay, so in this case, basically, we did do this mostly because it's easier to actually give what reviewer 2 wants and then say you should want it than basically not give it. So this is basically we did do this, but I want you to understand the asymmetry of how LLM research works. When it does something, irrespective of whether normal humans can do it or not, it's a plus point. When it fails, and if you can think of some humans who can't do it, then it's also a plus point for the LLM. It's not a particularly negative point for LLM. This is not how AGI is made. Okay, so that's the first question. By the way, the related question to this is in a weird sense. Here's a very interesting thing. We also did this experiment. I believe it was written in the paper, or if not, maybe it's there somewhere else. Karthik put it this way, basically also asked LLMs. Among the PDL domains, what domain does this remind you of? First. And it says blocks. Then you say, can you then solve it? It fails. You understand? That's your question. So if in fact I gave you something and said it is mystery blocks world, this mystery domain is actually blocks world, that's like a huge hint for you. In fact, LLMs were able to even notice that this crazy mystery domain is actually closer to blocks world among the PDDL domains that they know. And yet, next we say, now go ahead and solve it, it'll fail. There's this thing about the right hand doesn't know what your left hand is. LLMs basically don't know that they have both right and left hands. They can do one thing, they can do other thing, they're not necessarily connected. Okay, again, remember any of these studies are with respect to a particular point in time. You have, this was when it was written, this was the case. It was like 2 years back with the standard LLMs. So that's one of the points. Why do LLMs seem to perform better in 0 shot rather than 1 shot? Some people actually notice that in the results, consistently they seem to be having worse performance with 1 shot than 0 shot. And we saw it across the board. There is basically people always assume that giving examples helps, but but the only thing we can say here is that first of all, this is not only here, it's actually happened in other domains. And more importantly, what might be happening is okay, do I have a separate thing again? So what might be happening is that left to itself, it was about to just guess a plan, right? And what we are within that and putting an extra advice in the prompt makes it try to actually be dependent on the advice, not in a deductive way, but it sort of be dependent. And sometimes they can be at loggerheads. And all I can say is that seems to be the case, because if we just say guess, right? In some sense, guessing, especially for domains for which it has a reasonable amount of background data, I can't prove that it has. It would just be able to kind of, blur the solution out. But once I give, this is how I solve the problem, it actually confuses. This did happen across the board. There is we point this out in both the paper, and of course, I've been reading about this forever, and so there's some of this thing. So that's a good question, good point to bring up. How does GPT-5 do on this actually? Okay. The one other thing I wanted to say actually is, what is planning and what LLMs are good at? I'll come to this in a minute. But let's think about the following thing, because as I said, this is actually a very useful thing to understand. This actually, I said this in the class, but this is part of the ICML tutorial. So in a weird way, when I give tutorials on this stuff for like the conference, etc., they don't know the last 3 classes of stuff you already understood about what planning is, what logic is. And in the old days, everybody will know them, but now they don't. And so to some extent, I basically kind of bringing them up to speed in 3 hours, which here in your case, I'm taking like 6 hours by now, right? Because of the third class. Okay, so you might understand it much better that planning as used in the common parlance involves the planning knowledge, first of all. That is, what are the actions? What actions have what effects? What actions have what sequences? Etc. That's all knowledge. And then the generation and verification techniques, which involve how do you check that the plan is correct? What are the interactions between the actions? The stuff that we've been talking about in this. And as you know by now already, because there are 2 strands, one is progression, regression, etc., and the other is LLM-based planning. The progression regression stuff assumes that you wrote the domain. That's what you're about to write for the homework. So the planning knowledge is given by you. And they are focusing on the interaction resolution and the verification, etc., with respect to the model. And so it turns out that the planning, the ICAPS planning is basically PDL style planning. It's actually is assuming that the knowledge is given and emphasis on the inference of the plan. Plan is correct. This is classical computer science across the board. You first model the problem. With respect to the model, you want to get the solution to be correct. And it is, of course, a reasonable point that a correct solution with a bad model is still a bad solution. Okay, but that's how classical engineering computer science works. LLMs do an opposite because they're trained as they are. By the way, I did not actually do anything about my version of what LLMs do. At some point of time, I'll slowly do this separately, but you may have heard enough about it anyway. But LLMs, so obviously they're trained on everything I ever put on the web, and they have some kind of an approximate knowledge about it. So for them, knowledge acquisition is much simpler. They can at least approximately guess domain models. That's what I even said in the very first class. On the other hand, just because you have the knowledge doesn't mean stitching the subplans together correctly is easy. Remember, if you have, let's say, n subgoals, it's so much easier to assume that your training data contains a plan for each of the subgoals. Maybe a few extra plans for pairs or subgoals. It's very unlikely to assume that the training data contains plans for all possible, permutations of all possible lengths of subgoals. In which case, ultimately what it's going to do is it's likely to kind of take things effectively for what it knows and then splice them together. And that will fail when there are interactions between the codes. That's exactly the whole point of Sussman anomaly. That's exactly the whole point of mean sense analysis and serializability issues. This was my expectation. So how do you check that? We took blocks world and we made relaxed versions of blocks world. One relaxed version where delete lists are removed. That means all effects are only positive, nothing is negative. That means actions don't get into each other's space. The other is you can also remove the preconditions. It becomes easier and easier planning problem. And in terms of search. And we basically point out that if you compare to non-relaxed versions where green is the correct and red is incorrect, by more and more relaxed versions, LLM does the plans correct, as judged by the verifier. Do you understand? The verifier is going to be, if you delete this, you check whether the thing is correct with respect to the domain model. That's it, right? So basically, if there's no delete this, then there won't be Sussman anomaly, for example. Okay, so that sort of explains to you that in the world at large, there is exactly, one of the things that you don't think about in the classical planning these kinds of courses is you don't think about solving every possible problem that hasn't yet been modeled. You model a problem and then you give it to the lab. With the LLMs, basically, they kind of have an approximate model of the universe of stuff that we have written. But that doesn't necessarily mean that they can do search. So that basically, I love this. I wind up giving it, like I gave a talk to Montreal, a cognitive science workshop on Tuesday. I use this slide too. It's one of the things that I'm particularly fond of because it makes the point that it's actually, LLMs are actually very standard LLMs. When I say LLMs, standard LLMs are actually very good at doing planning when planning is not needed. Right? Because when planning is not needed, once you give the model, if in fact any subplan for any subgoal can be connected with any subplan for any other subgoal, then the thing becomes actually the harder issue would be, I wish I had this other slide too, maybe I'll show it in a minute. The harder issue would be to essentially just know what possible actions are there. How many of you know MacGyver? MacGyver, okay. MacGyver, okay. So MacGyver is this show, people from India, Jugaad. Okay, so MacGyver is the show about Jugaad. Right? Here you go. So essentially, there will be all these things that we think is not possible to solve this thing, and then he will use things in non-standard ways and achieve the goal. A classic example of a MacGyver planning problem is, imagine you are, and you're basically in your home, and essentially your heating comes out. It's a dead of winter, which is not never happens in ASU, but the heating comes out. Then you can put the refrigerator in the high and sit in that room. Nobody in their right mind buys refrigerators to heat rooms. But knowing thermodynamics, you know that if refrigerator is heating the room. You see what I'm saying? That's MacGyver planning, essentially. Using things, standardized things. Basically, that's why the word jugaad means a lot to people from India, which is essentially that's not the way you're supposed to use that. For everything, there should be a tool. That's the way people assume that there's a standardized tool. And you're saying, well, I can just use whatever I have and jerry rig something that will actually get me the goal. LLMs are actually good at that. Because they can guess random things, basically there's so much knowledge. So in fact, I wish I had the slide, I'll send it to you after this, but I say, if you want to argue that LLMs can do planning, and if you want to argue that LLMs can't do planning, do what I did, which is take a domain, which is actually pretty simple, but there are interactions, and they have. If you want to argue they can, and I want to be impressed with them, then take a domain where you don't even know what the actions are. There's just so many possible actions. There's no such thing as even a domain. It's a common sense thing. I just give a plan out of the hat. And then classical planners obviously can't keep up because they'll say, first give me the model. And also make sure that the plan that you are giving, it turns out that there are not too many interactions. Then actually LLMs will win very well. So you can argue both ways. You just need to know what they are good at. That's a more constructive way of understanding what it's good for and what it's not good for. And then what is the other one that I wanted to say? I forget. I don't know. Where am I going? 1 second. I don't know why I went this far. Yeah, I went this. Okay. One last thing I want to say, actually. So many other slides. I'll show you the one I told you about when to assume that they can do planning, etc. and send it to you. But this one also I want to bring up because you'll understand this. Fine-tuning on LLMs. Everybody wants to make LLMs solve new problems by fine-tuning. I want to give you a caricature of that and make you understand what is involved in a computational sense. Okay? You guys can understand this. The Go5 way, which is basically this class, basically the doing the planning by giving the model way of solving the block-solved planning problems, is you get the domain model that you're going to write by Monday. You have a combinatorial research planner that you're learning about, progression, regression, plan splice, whichever one you pick. Give the problem to the planner and go on. That's Go5. But you won't get any new papers on that because it's been done in 19th century. Okay. Right? The Llama, I call it Llama. This is basically LLM AI. Sort of particularly making tongue-in-cheek joke about it. Okay. But it's true, essentially, what fine-tuning does. What does fine-tuning do? Lots of people actually have tried to show LLMs do better in block-solved planning. And lots of papers are there. And those kinds of papers, basically, many of them, what they will do is they take the domain model. Yeah, right? Are you right? They get a combinatorial search planner that you're going to learn about in this class. Make 1 trillion block-solved planning problems. Make the planner solve them all. Fine-tune GPT-4 with the problems and the solutions. Alternately, index the trillions of solutions via vector database for a later rank, if you are even number. Okay, but let's do this like a fine-tune. Okay, and then have fine-tuned RAG GPT-4 guess the solution for the given problem, which is helpfully in the same exact distribution. In the sense, if you fine-tune with 4 to 15 block problems, you'll only give 4 to 15 block new problems. 17, oh my God, that's way too hard. 29, my God, never heard about it.
That GPT like 25 and that.
What?
I said, whenever the new like GPT 25 comes out, you'll be able to do it.
That's it. That's a different story. Then you don't need to. Then one of the points is that then you can actually avoid taking any classes and wait for some argument to do things to make us be available. Okay. So have the fine-tuned RAG GPT-4 guess the solution for the given problem. Ensure the correctness of the guess with an external validator, which also was actually supplied by the verifier. Because LLMs can't actually verify themselves. There's another paper that we talk about there. And if by luck it guesses right, write a Heuristics iterate saying fine tuning seems to happen. Even as I speak right now, there's a new paper that came into my, Google Scholar keeps telling me stuff about planning stuff. And so there's somebody else, a good friend of mine, unfortunately, many of these people are good friends, so I hope they don't listen to this stuff. They said, to unlock the planning potential of LLMs, because before it used to be zero-shot planning abilities. Now, unlock the planning potential of LLMs by fine-tuning with diverse training data. It's not any trillion examples, my friends. You should get trillion examples that are actually be a lot more connected to the kind of test that you will do. That is actually standardized LLM fine-tuning. I'm not making anything up. By the way, very important to understand that if you disagree with me technically, you will get an A+ in this course. Don't worry about disagreeing with me. If you sleep or check your cell phone, you will get a D-. That you should worry. Okay, so I don't know all the answers. I want you to be engaged. And that's the part of being at the edge of the research. My point is, if you can actually come back and say, this is unfair characterization of fine-tuning, I would love to hear about it. And I would also argue that when we come back, I'll show you at some point or later, that the difference honestly between reasoning models fine-tuning and standard model fine-tuning is, instead of just taking the solution and the problem and the solution, take the problem, trace on the solution, and fine-tune. And then in the inference stage, it will give some amount of trace, which kind of looks like it is doing some kind of planning reasoning, followed by the solution. This has been called post-training. But the reality is, the signal is coming from the external validator, which is about checking whether the plan is correct or not. That you are understanding here, how to check the correctness of a plan in a progression and regression. The very idea that you have RLVR, what does RLVR mean? RL with verified reward. Who is giving verified reward? It's not that DeepSeek was running plans in the real world and checking if it is failing or not. It has a rule-based reward giver. What is a rule-based reward giver? It's a symbolic verifier of some sort, or a learned verifier of some sort. Now, my guess essentially is these kinds of things, it's not surprising. In computer science, you know that rather than wait for somebody to give you a problem and solve it after they give it, if you solve all possible versions of that problem beforehand, when they give the problem, you can just look up. This is what is known as memoization. Did I mention the Google roadmap thing, Google map thing? What? Yeah, basically memo map thing, etc. For example, essentially stuff using a star search, a path from S to G, you can do all pairs shortest path algorithm beforehand. And then when people give, like in SNG, you just look up. So that's the extreme. The reason you don't normally do it is because why solve a single problem by first solving trillion problems and then saying that I'm solving it? That's exactly what fine-tuning is doing. So it better be the case that the money you spent in the fine-tuning is giving you more than a Heuristics paper. I understand Heuristics papers are worth more than a weight in platinum. Right, and so it doesn't really matter how many GPU hours you wasted in fine-tuning if you actually can show slightly better accuracy. But if you are a startup and you actually want to stay in business, and instead of hoping that you will be acquired by some other sucker, the greater sucker theory in the pyramid schemes, right? Right? Then you better be the case that the money you spent in fine-tuning is more than made up because you are actually able to quickly solve these problems in the inference stage. Is anybody really checking it? No. When will it get checked? when economics turns against. You are saying again, it's useful. It's a great technology, especially since it exists. Why won't I use it? But you need to understand, especially with things like fine tuning. Everybody says, "Oh, I have a new problem. I just fine tune LLM." Well, how did you fine tune? Either, in fact, many of the cases, basically, people will say people make the answers and they'll fine tune. That's even worse. Because in those cases, you don't even know how to actually verify whether the solution is correct or not. It looks like good solution. For once, for there is verified, you actually at least can talk about real accuracy. And this is the reality of fine tuning. Understand? Okay. Thank you for your extra time today. And by the way, I did take attendance. So if you are here, please come and tell me if you forgot to give me your name. Thank you. Just 1 second. Yeah. What? No, why?
Just,
Oh, 1 second. Anybody with attendance? Last
Okay. Just to say for last class, I emailed you already.
That doesn't matter, not right now. I'm good, man. You're done now. Anybody else? I took your lead, yeah.
Just want to make sure, set up with the video.
Yeah, it's okay, yeah. Thank you. Okay. Anybody else? Okay, good. Okay.
So when I was reading the research paper, I had some curious questions. I don't know if these are dumb.
Mhm.
So I had these like 4 questions.
Did you post it there?
Yeah.
Yeah, I posted. I'll look at it at some point of time
Okay.
and then look at it. Yeah.
So regarding the PDDL prompts, I thought that I don't know, after 3 hours class, maybe I'm feeling little.
Mhm.
So I thought that the performance is better for 0 shot than the 1 shot because the example in the 1 shot might cause sometimes confuse the model or may cause it to imitate a pattern that doesn't transfer well.
Possibly. Yeah, but I mean, those are all qualitative explanations. It is clear that it's not doing it right, but the problem is actually explaining why LLMs do what they are doing, either for profit or either by explaining why they fail or explaining why they succeed, is a trickier thing than people expect. Plausible explanations are dime a dozen.
Okay.
Okay, so I think this is fine. That's a reasonable explanation. But if you really want to show this is a scientifically valid explanation,
No, I'm just asking if it is.
I don't know, because some of these things I don't know the answers to yet myself. I mean, as I said in today's class, essentially, my expectation is that the extra thing, that's kind of in line with what you are saying, which is my expectation is that the extra example essentially sort of, it already is about to output in a certain way, and then the extra example actually confuses because it also becomes a soft constraint on the conditional distribution of the tokens it's going to give out. That's pretty much, saying something, something that's actually supposed to be helpful can actually worsen its performance is basically what we are seeing.
Yeah,
That's basically what I was saying. And my sense is I don't remember whether this happened for mystery domain or not. My recollection is it was more of an issue for blocks world than mystery blocks world. Because in essence, you have like a more of an intuition as to what the correct answer is from the training data. And mystery domains don't have that much of a training data. And so it becomes harder. So that's my guess. But I never wrote a paper actually evaluating whether it is the correct answer or not.
So regarding the mystery domain problem, Professor, so like obfuscating the data, I mean, and training the LLM on that, I mean, 50% of the normal data and 50% of the obfuscated data, will that help the model perform well? I mean,
No, we are not training anything. Remember, much of this paper is not about training at all. did not train the model. That's an entirely different thing to do. We didn't find, there was some small fine tuning we did where we didn't do the mix of the thing that you're talking about. Most of the paper really is about out of the box GPT-4. How is
Yes.
it doing? And so we are not retraining it. We're just taking what it is doing. So quote unquote, what the heck they call the ICL, in context learning, which is just prompt engineering.
Okay.
Right? And training brings up an entirely different set of issues.
Yeah.
I mean, that's more like what I was just saying. This friend of mine apparently wrote, their students wrote that diversify the training data so that the planning will be better, etc. I mean, at some level it looks okay, but whether or not that is an actually interesting idea depends on how you execute it.
Okay.
Right. So, I mean, it's a reasonable, for example, it's a reasonable class project to see if in fact mystery domain performance would have improved. Of course, I mean, mystery domain performance obviously would improve if you give some mystery domain examples. The real question is, what are we going to say? I mean, like the diversity aspect is, if you train a block sword, so yeah, like a bunch of things like, you can take an LLM and just train it purely with mystery domain, then it might do worse on the blocks world, normal blocks world. And then you can say, I train it with both, fine tune with both mystery domain and blocks world and see what happens. I mean, these are all okay, reasonable projects to look at for a class level.
Okay. Just one more. So the thing is, the paper actually shows that fully obfuscating names significantly reduce the LLM planning performance. So what if we only half the
That's what you're saying. That I don't know, it depends. I mean, we didn't do it. You can do it. I mean, again, for anything basically
for the
the domain model, it's no,
yeah,
not
for
that
the
no, there's no training data. You're confusing. The paper actually only gave mystery domain just once. It didn't train the model. The model know what the model knew. What the model knew, what the model knew. Right. So if you are talking about combining blocks world and mystery blocks world, then you need to give something called MB world, which has some names from pick up, put down, and some names from like feast and etc. That's a very different thing. And then you can see, I mean, we didn't do it. I don't know how interesting or not interesting it is, but certainly we didn't do it.
Okay. So these
We
are
just purely fully obfuscated it.
okay. So these are like something we can do maybe.
Possibly you can, as a class project, yes. As it is interesting at a research level, I don't know. Again, honestly, I'm mostly disappointed with most of the research that happens that actually gets published in NeurIPS. So maybe it'll also be fine with NeurIPS, but as a class project, of course, surely.
It can be done.
Yeah.
Okay, Professor. I'll look into it.
Sure.
Thank you.
So I had a question regarding the performance LLM has with zero shot and one shot. Can we infer that if the knowledge is outside its domain, if it is a very contextually heavy domain, like let's assume a medical domain, half of the jargons the model does not know about, can we infer that giving it extra context will make it more confused?
Again, I don't know. Again, my problem honestly is these are all, but please don't take this personally. I mean, this is all, it's not a crisp statement. What does context mean? First of all, the word context is one of the most overused words in LLM literature.
Yeah.
Like anything you think, yeah, it's a context that is needed. What the heck is context, right? And one of the issues would be, what if what you're doing as part of the changing the prompt is giving away the solution so that it'll do better? And so is there something, it's not that what you said is a partial specification of what project you might do. That is consistent with both bad projects and good projects. Okay.
But I was just confused about what you said, that if you give a prompt, it might get more confused. Is it related specifically only to planning?
No, it is nothing to, it is, okay. Actually, it's a very good question. I guess maybe we should have spent more time on this because you have questions on this. But there is an interesting thing that when the prompt goes against the training, it will do the training. So for example, consider the farmer goat wolf problem, where I actually change the domain, change the specification, and I say there is no wolf. It will still give the answer to the farmer goat wolf. Is this context? No. Basically, the prior information, it needs to consider how the prompt and the prior information that's baked in have to actually be interacting. And sometimes the LLMs are just bad at it sometimes. Do you understand what I'm saying? So on one hand, it should be clear that I gave the correct prompt about what I want, and you're still giving me the solution for the stuff that you know. Do you see what I'm saying? So it's not about planning at all. It's more about whether the domain is known to it or not, whether the kind of domain is known to it or not. If it is well represented, overly represented in the training data, then basically the prompt has to go against the training data. You're about to say, you're more likely to complete things that come from the training data, and then the prompt is actually pushing against it, and that may worsen things.
Obviously, the performance
That's,
would
yeah,
be
yeah.
worse.
So the performance is not that LLM is trying to be correct or wrong. It's just doing the token prediction. And you are trying to, basically count the tea leaves and then write papers on that to some extent. So that's basically it.
Thank you,
Okay.
Professor.
I have two questions. So the first for the human experiment for Mr. Boxford, what is the plan translation stage do? Because it's not translating from Boxford to Mr. Boxford. It's like they're saying what's the effect of the action of, or what's the effects for these actions in this plan, and that's the phase.
I didn't understand what you're saying.
It's on the mystery blocks world side because it said like their participate in like two phases. Like first like plan writing and the second is plan translation. And my question is what is plan translation if it's not?
I don't remember. I think plan writing is mostly what I was telling you about. I don't actually remember the answer for that. I mean, send me a message on the Piazza.
Okay.
I'll try to get the extra information on that.
And this,
Yeah.
Second, I have a project from another class. I think it's related to this because I was training large language models on like a bunch of chess puzzles, and like actually found even if you can separate the positions so that it's given just new positions never seen before, it can actually solve like certain types of puzzles. But then if you test it, like let's play a full game, it can't because it's it doesn't have those positions from like a position is training. And I just thought it was interesting.
Yeah. I mean, there are many, many things that are interesting because these are alien things, and basically people try to overload what they think humans do, humans with that kind of a knowledge will do. And that's just not true, honestly, with LLMs. And so it's a question of, I mean, these are all observational stages. Actually, there is a CS, remind me in the Piazza, I'll send you guys a CSCM blog piece I wrote, which says AI as an research natural science. Computer science used to be very mathematical and theoretical. With the new AI, it's become, basically, whereas zoology, for example, will go into the wild, find some Amazon jungle, some funny animal, poke it and see what it does, write a paper. We are now that, except that we grew our own animals. We just didn't know how those animals actually act. Basically, we trained these large models. We have zero clue as to what they're supposed to do. And we are poking them and writing multiple papers. Okay, and that is important to understand. And essentially, there is really no theory about most of these things. I mean, again, I'm not mentioning them. Like I was basically in this workshop on Tuesday with a bunch of cognitive science folks, very, very well-known people like Alison Gopnik, who basically is like a very well-known child psychologist, lots and lots of books, etc. They're clueless. They have no actual idea. Everybody is just like in the blind trying to make random analogies, about what LLMs might be doing.
And my third is kind of related to, do we care even if they can't reason? Because if they are good pattern matches, can you not just it's like the Chinese room argument, kind of like
yes. The point is, if, as I said, it matters in as much as if there is a wrong solution and you execute it and you get into trouble, then it matters. Otherwise, it doesn't. Right? I mean, that's why, like, do you care that they are actually not writing, they're not writing coherent English? Nobody cares because, in fact, nobody is reading most of the junk that they're writing. Right? I mean, the whole email sending has become, you have 3 bullets, you ask ChatGPT, here are my 3 bullets, write into 5 pages, and you send 5 pages. And then the other side, you say, make it into 3 bullets, and they'll make it into 3 bullets. So we could have saved a lot of network traffic without actually doing ChatGPT both sides, but we feel good somehow, right? In those kinds of cases, how does it matter? The fact, but basically, if on the other hand, it is actually guessing a plan, and the plan is not correct, and you're actually executing it without checking, then you deserve what you get. right? I mean, it's an extremely useful tool as an idea generation tool for with humans in the loop, with the human actually taking the blame if something's goes wrong, right? But on the other hand, if it is end user facing and end user is clueless, or actually it's directly connected to the world, then it does matter that if it is wrong, it's only plausibly right, then what happens? That's the whole point. I mean, the whole point about engineering is sometimes it flies, sometimes it doesn't fly. How does it matter? That's not how we make planes. We actually try to give some guarantees, right? And that is the part that is missing right now, just simply missing.
Thank you.
Okay.
I'll try to remember on Piazza.
Okay, sure.
The answer is completely obvious for us.
Which one? Oh, okay, what you're about to ask. Okay. Mhm.
So if planning is like reasoning about the actions to take.
Yeah, that's a kind of a
Yeah.
reasoning, essentially.
So why bother like trying to make LLMs better at planning? in a
No, because
sense?
basically everybody says that they're good at everything.
But it's all based on pattern recognition, so
No,
why?
no. Again, my point is, first of all, I want people to understand. I mean, again, from at least my group, that's the thing.
Mhm.
It's you should avoid being either Gary Marcus or the hypester,
Mhm.
right? I mean, like nothing will ever impress me, doesn't help,
Mhm.
right?
Yeah.
Basically, it's the word pattern matching is just a big word. I don't exactly know what it means. I mean, there are reasoning models actually. If something is like 99.9% of the time correct on blocks world problems up to like 15 blocks,
Mhm.
how does it's still quite impressive? How did you get there? Right? And that's what reasoning models do. For example, O1 gets you there.
Mhm.
Do you understand what I'm saying?
Yeah.
So my thing is, I want to actually, I would avoid both extreme sides. I want to understand what the technology can and cannot be depended on.
So like, don't be too skeptical or.
No, it's not skeptical. Skepticism is always good.
Yeah.
Skepticism is good.
Mhm.
Okay. Don't be just prejudging things.
Yeah. Mhm.
Skepticism is I withhold judgment, but I'll do experiments.
Mhm.
Prejudice is I made up my mind. You don't need to tell me anything.
Mhm.
Right?
Yeah.
So saying LLMs are pattern matches, why do I care, etc., that doesn't make any sense to me, because obviously we don't completely understand their pattern match. Whatever it is that pattern matching you're talking about, you don't completely understand what it is in a theoretical sense. And as a computer scientist, if you're depending on if these things are in our world, we need to have some understanding of what can and cannot be said about these technologies.
Mhm.
That's worthwhile doing it.
Okay.
Right? And in particular, of course, I mean, I started this mostly, I mean, the reality is in 2022, when we started looking at this, there was no reason to even, just like you said, basically, why would I never considered that LLMs will do planning. But first of all, you have to realize that the technology is going much faster because the entire world has become monoculture now.
Mhm.
Right. And so the technology is progressing much faster than anybody expected. So GPT-2 to GPT-3 is a much bigger jump. GPT-3 to 3.5 is a bigger jump. 3.5 to 4 is a bigger jump. Even as this stuff was going on, I never really believed planning is likely to be possible. And it's not worth my time to show that they can't do planning.
Mhm.
I only write this paper almost tongue in cheek. I mean, not me, I mean, my students wrote, because so many people are thinking it can be done, so show it. Like, for example, is it worth showing astrology is not science? Most reasonable people understand astrology is not science. Why waste time? But on the other hand, if you're in India, maybe it is worth showing because there's a whole bunch of people believe astrology actually works.
Mhm.
Okay, so to some extent, sometimes the worth of showing what might be obvious to Einstein is still worth showing to the general population because they still haven't quite got it,
Mhm.
essentially. So that's pretty much what we did. And in fact, people in planning, when I did this, people in planning, I have a very good friend, Dan Weld, who's also in planning. And, I tell these stories to my students, we are basically very frank with each other. And, basically this paper that got into Neurips, basically Dan looked at it and said, it's a good paper, but do you really need to even write this?
Mhm.
But joke is on him because it's a pretty well-cited paper because enough people, there are so many bozos who think plans, even with this, that LLMs can do planning.
Mhm.
That is worth pointing out what is and is not possible.
Okay.
If I'm only writing, there are two things. I mean, I told Dan at the time that, Dan, if I write only papers that will impress you and you write papers that impress me, then we don't have to write many papers at all. which is like a way of putting him down too, because he was writing a bunch of papers that were obvious to me. But the point in general is you don't write papers for just one person. In general, to some extent, sometimes there is a widespread misunderstanding that somehow planning will just come out. And this is like egregious misunderstanding. You have to understand that. So one of the weirdo things is there were people, I mean, again, this is in the last 4 years when standard LLMs actually could not do planning. They were like basically getting zero performance on mystery domain. And yet people are saying they can do planning. And then finally they did these reasoning models which are very, very different. They're like, there's a huge post-training thing. There's a lot bigger synthetic database training, etc. And they actually solve planning there. And now they say, now these are reasoning models. So I would honestly argue, why would you, if in fact LLMs are doing reasoning already, why would you need reasoning models? You obviously knew that they weren't doing it, but it's easier to just claim that they do. And then people will still, that's why all these bad papers, unfortunately, get lots and lots of citations. And that's what I think I may have said this in the class, that if I show that your paper is wrong, I should get all your citations. I mean, I would like to get some of those chain of thought paper citations because we showed them that they're actually wrong in several cases. But that's not the way it will happen. Basically, people will say chain of thought X has been shown to not work, raw. And so they also got one thing, right? Unnecessarily. So bad ideas stay for long enough time. Of course, I mean, ether finally died. Right now, you still no longer, nobody ever writes ether about ether in physics. But at the time of, the transition time, which we are right now, they were citing ether stuff and saying maybe it's not needed. Right? Okay, so that's a long-winded way of, and again, understanding what is and is not possible, given that the entire world's resources are being directed at these kinds of pattern matchers, whatever the pre-trained data stuff, where you're making both the data and both extra data as well as existing data. It's not as obvious. Saying they're just pattern matchers and moving on is actually not going to be good.
Okay.
Right? I mean, that would be kind of, that's more like Gary Marcus' way, and I don't think that makes sense.
Okay.
You need to look at what's happening and kind of push back on both ways. So you should be hated by both ends. Where you're right if both far right and far left hate you, then you're right. That's the way I think about it. So, and similarly, if both LLM haters and LLM boosters hate you, then you're in good shape. So you must be doing something right. Okay. Yeah.
I have a general question. It's like, how can we integrate computer vision with the planning?
What does that mean?
Okay, so I have been working on computer vision projects with ML and AI. So I'm like, I want to integrate planning also along with the computer vision.
I mean, that's not the issue. I mean, the normal way that would be like robot planning normally actually combines both vision and planning. And there's stuff like VLA and VLS, etc. Those are connected. I won't go too much into them. I mean, this class doesn't touch vision as much.
Yeah, it's like I took this course for like planning methods. I wanted to like.
I mean, I think what I'm saying is it's not obvious. If I know obvious things, then there are things, obviously, things like robot planning, etc., are connected to both vision and there's some stuff that is done by like Feifeli's group that is relevant because she kind of combines both vision and planning stuff.
Okay, so is like you mentioned robotic planning and all. So can we use the fine-tuned or something planned LLM which we
they use it left and right. I mean, the whole place is full of robotics. People are full of this kind of nonsense, honestly.
Yeah.
I mean, like these bad papers are written everywhere. You should write yours too. I mean, don't be stopped by me. Essentially, what I'm saying is, I just think they're bad papers, but that doesn't mean anything, right?
Yeah,
They get published. So,
I do have a research experience. So for the next semester, I was planning to get thesis. So I'm exploring the domains whether to focus.
You are in what program?
I'm from master's CS.
Oh, okay.
So I want to complete thesis. So I was like exploring the domains.
Okay. Yeah, to be completely honest, for masters, you just go to somebody, expect if they take you, just do what they want you to do. That's it. You don't have the luxury of let me figure out what a thing is and then go and ask somebody, why don't you advise me? Because none of us will do. I mean, nobody who's worth their salt would advise random people on topics that they want to do. I'm just telling you how the world works.
Yes, I agree.
Okay. Even PhD is very hard. that
Yes,
way.
and
So
my reason was to talk to you was like, if is there any opportunity?
that's the way. I mean, what I'm saying is, that's not the
I'm
way
not
for
getting
me
it.
it works. I mean, for me, it's like you say something that catches my attention, I might think more.
I-
That's the kind of thing.
Yes,
That's it.
I
Yeah.
agree.
So yeah.
So I was like, I will get.
Yeah, and that's
contacts.
basically, and then you figure out what people are doing, you try to make connections with them, and if you're taking a course, if you say something that catches my attention, then that might lead to something. What's your name?
My name is Manav.
Manav. Okay, good.
Thank you.